You have never been still, not for a single second. You're riding a spinning planet inside a rotating galaxy, built from particles that carry spin like a signature written into reality. So why does almost everything in the universe rotate, while the universe as a whole seems to add up to nearly zero? Where does all that spin come from, and where does it go? In the darkness between stars, rotation is the universe's quiet fingerprint, etched into matter, light, and time itself. Follow it long enough, and it stops looking like motion and starts looking like design. Across the cosmos, spin behaves like a law with a memory. Once a system begins to turn, it keeps the account. Yet nature is strangely strict about the bookkeeping, allowing speed to change while totals remain stubbornly conserved. In this film, we follow that invisible ledger from the familiar to the extreme, where turning becomes pressure, stability, magnetism, even the power behind some of the brightest beacons in space. We begin where intuition fails, with a calm world that only feels calm because its motions are shared and smooth. From there, the story tightens around a single idea. Angular momentum is not merely a quantity we measure, but a consequence of deep symmetry. When symmetry holds, the universe refuses to forget what has been set in motion, and when symmetry breaks, even slightly, gravity can amplify the smallest twist into a dominating structure. Then we cross a boundary where rotation stops meaning what it meant a moment ago. In the quantum world, spin is not a tiny sphere turning in space, but an intrinsic label, an identity that determines how particles respond to rotations at all. It shapes atoms, chemistry, and the magnetic order that can persist across billions of aligned moments, and it forces the universe to choose from discrete outcomes where classical physics expects a continuum. From that foundation, we climb back upward into the realm of collapsing clouds and newborn stars where energy can be shared as heat and light, but rotation is harder to dispose of. As matter falls inward, the same conserved budget drives it faster, building disks, launching jets, and setting the stage for remnants so compact that a single second can contain dozens, hundreds, or more turns. Some of these objects will reveal their spin through clocks of radiation, others through the warping of space-time itself, signatures that can be read across unimaginable distances. We widen again to the scale of galaxies, where rotation is no longer a solid body's turn but a vast choreography of orbits. There, the motions of gas and stars trace a hidden scaffold, and the speed of a spiral's outskirts refuses to behave as simple gravity would suggest. Rotation becomes a tool of detection, and the act of measuring it begins to map what cannot be seen. And finally, we return to the earliest light and the largest patterns, where the universe offers no obvious axis and no preferred direction. The evidence insists on a profound balance, countless local spins, and yet a cosmos that appears in total astonishingly impartial. The tension is not a contradiction. It is a clue, pointing toward how symmetry, chance, and cosmic evolution can fill the universe with turning while keeping the whole remarkably even. What you're about to see is a journey through scales, from the smallest rules to the largest structures, guided by a single recurring motion. By the end, rotation will look less like a feature of certain objects, and more like the hidden architecture that makes a universe like ours possible. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from everyday stillness to conservation, from quantum spin to collapsing stars, then outward to galaxies and the early universe. Each step narrows the mystery, until the cosmic ledger finally begins to balance without granting the universe a single, global direction. Stand still for a moment and the world feels quiet, flat and motionless, as if the scene has been pinned in place. Your feet seem planted, your room seems stable, and the sky seems fixed in a way that feels almost moral. That feeling is useful for living, because it lets the brain treat the environment as a reliable stage. But it is a deep illusion. Nearly everything we can measure is turning, and it is turning all the time. Begin with the ground beneath you, which looks like the firmest reference point you will ever have. Earth rotates once every day, and at the equator that means about 1,670 kilometers per hour. At mid-latitudes it is slower, because the circle you travel each day is smaller. You do not feel this speed because you, the air, and almost everything around you share the same motion. The rotation is also steady, so your inner ear gets no warning from acceleration. Stillness is what constant motion feels like when nothing changes. If the camera could hold on your body while the planet turns, the illusion would become visible. City lights would trace arcs, clouds would slide in long ribbons, and the horizon would tilt by a fraction of a degree each minute. Above it all, the stars would appear to wheel, an ancient observation that helped early astronomers suspect a rotating Earth. The sensation of a fixed sky is a trick of scale and habit, not a property of reality. Zoom out and the daily spin becomes only the first layer of movement, like a small gear inside a larger machine. Earth also orbits the Sun at roughly 30 kilometers per second, which is about 108,000 kilometers per hour. The path is not a perfect circle, but the speed stays in that neighborhood as we sweep around our star. The Sun's gravity supplies the inward pull, and inertia supplies the urge to keep going. The result is a perpetual fall that never quite lands. In a visual sense, orbit is a kind of controlled miss. If Earth stopped moving sideways, it would drop inward toward the Sun. If gravity vanished, Earth would fly off in a straight line into the dark. Instead, the two tendencies balance, and the planet draws a looping track through space. Even the seasons, which feel like changes in weather and light, are embedded in this larger motion. Zoom out again and the Sun is not a fixed anchor either, despite how central it feels from the surface of Earth. Our star orbits the center of the Milky Way at about 220 kilometers per second. The solar system rides that galactic current, completing one circuit in a few 100 million years. We call it a year when a planet returns to its starting point. The galaxy keeps a longer calendar, and we are inside it. That galactic orbit is not just a number, it is a reminder of scale. The Sun has made only a few dozen trips around the Milky Way since it formed, while life on Earth evolved from single cells to telescopes. If you could draw the Sun's path, it would look like a slow, majestic sweep through a crowded disk. Stars pass near one another, clouds of gas drift, and gravity constantly nudges trajectories. The solar system is not parked in the galaxy, it is carried. Even the Milky Way itself is a rotating structure, a vast disk with a bulge at its center and a halo of older stars around it. Its disk turns with a period on the order of 200 to 250 million years. Stars closer in move faster, and stars farther out move slower, but the overall pattern persists. The spiral arms are not rigid spokes. They are long-lived waves in a rotating sea of stars and gas. Those arms are more like traffic jams than painted stripes. Gas flows into a denser region, compresses, and can ignite bursts of star formation. Then it flows out again, leaving behind clusters of bright, short-lived stars that outline the arm for a time. When we see a spiral galaxy in a photograph, we're catching a dynamic pattern in mid-sweep. The beauty is real, but it is not static, so the opening claim is simple. At human scale, planetary scale, and galactic scale, motion is the rule and rest is the exception. Yet the deeper claim is stranger, because it is not only about what happens, but about what is allowed. Rotation is not just common. Rotation is protected by one of physics' most reliable accounting rules. To talk about that rule, we need to separate two ideas that share a word and often get blended together in casual speech. Rotation in everyday life is motion through space around an axis. A bicycle wheel rotates, a planet rotates, and a galaxy rotates, and we can picture parts moving around. Spin in quantum physics is different in kind. It is an intrinsic property of particles, not a tiny sphere literally spinning like a top. This distinction matters because our intuition keeps trying to build a picture that is too small and too mechanical. Electrons are not little marbles with painted arrows on them. When physicists say spin, they mean a built-in form of angular momentum that behaves according to quantum rules. It has measurable consequences, but it does not require a literal surface rotating in space. The word is historical, and the mathematics is the real guide. Electrons have spin, protons have spin, and even photons carry angular momentum. Those spins show up in magnetic behavior, in atomic structure, and in the way light interacts with matter. The math treats spin as angular momentum, but the picture is not a miniature rotating ball. Quantum spin is built into the particle's identity, like mass and charge. One vivid consequence is that spin helps organize the architecture of atoms. Electrons occupy quantum states, and their spin is part of what distinguishes one state from another. The patterns of chemistry, why elements bond, why materials conduct or insulate, depend on these quantum rules. Magnetism, too, is not just a macroscopic phenomenon of bar magnets. It emerges from countless microscopic spins aligning, resisting, or cancelling. Across these scales, one quantity keeps appearing like a signature written in different handwriting. It is angular momentum, usually written as L. For a simple rotating object, it depends on how much mass there is, how far that mass sits from the axis, and how fast it turns. In the simplest cases, you can think of it as rotation's amount, combining size and speed into one conserved total. Change any of those ingredients and the rotation rate can change, but in an isolated system, the total angular momentum does not disappear. In classical mechanics, the key idea is torque, the rotational cousin of force. If no external torque acts, angular momentum stays constant. Friction, tidal forces and collisions can move angular momentum from one part of a system to another. But the sum, when you count everything involved, remains stubbornly fixed. It is a ledger that balances even when the details become messy. This conservation is not a coincidence or a convenient approximation. It is tied to a deep symmetry of nature, one that is easy to state even if its full meaning takes time to absorb. If the laws of physics do not care which way you face, then rotation has an associated conserved quantity. This is a preview of Noether's theorem. Stated in plain terms, continuous symmetries imply conservation laws, and rotational symmetry implies conservation of angular momentum. There is also history behind that insight, because it did not arrive all at once. Early mechanics, from Newton onward, revealed conservation principles through careful bookkeeping of motion. Later, mathematicians and physicists learned that conservation is often the shadow cast by symmetry. Emmy Noether formalized that connection in the early 20th century, and it became a cornerstone of modern physics. The universe keeps its promises because the laws have a consistent structure. That link matters because it explains why spin is so stubborn, and why rotation appears whenever systems collapse, collide, or rearrange. When matter moves inward, it tends to spin faster, because the same angular momentum is now packed into a smaller radius. The universe can trade shape for speed, but it cannot easily erase the total. You can slow rotation by spreading mass outward, or speed it up by pulling mass inward. Either way, the accounting holds. You can see the rule without telescopes or particle accelerators, using nothing more than your eyes and a well-chosen demonstration. Watch an ice skater begin a spin with the arms extended, blades carving a tight circle into the ice. When the skater pulls arms inward, the rotation rate increases dramatically. The skater did not add a motor. The skater changed the distribution of mass around the axis. In slow motion, the effect becomes almost eerie. The skater's posture tightens, the shoulders draw in, and the world seems to blur behind them. Energy shifts form, but angular momentum stays nearly the same because external torques are small. The speed up is not magic, it is geometry. The radius shrinks, so the rotation rate rises to keep the same rotational amount. The same thing happens on a spinning stool with weights, a classroom experiment that feels like a physical riddle. Start turning while holding weights out to the sides. Pull the weights inward and you speed up even if the stool is nearly frictionless. Push them outward and you slow down, as if time itself thickened. The total angular momentum stays nearly constant, and the body adjusts its speed to keep the ledger balanced. This is the first key beat of our story. Angular momentum is conserved with astonishing accuracy, from toys to planets to galaxies. We can predict how fast a collapsing cloud will spin, how binary stars exchange rotation, and how spacecraft stabilize in flight. We can measure tiny changes and trace where the angular momentum went. The bookkeeping works. Engineers rely on this every time a satellite turns to face Earth, or a probe steadies itself in deep space. Reaction wheels spin up in one direction, so the spacecraft rotates in the other. Astronauts in microgravity can twist their bodies and reorient, even without pushing on anything external. The motions look effortless, but they are constrained by the same accounting rule. Conservation is not an abstract principle, it is a practical tool. Now the tension enters. If angular momentum is so easy to keep and so hard to destroy, why does the universe not look like one giant spinning top? On the larger scales, the cosmos appears isotropic. It looks roughly the same in every direction, with no obvious preferred axis. The sky does not announce a universal North Pole. This is not just a philosophical preference for symmetry. Astronomers have searched for signatures that a global rotation would leave behind, because rotation would not be shy. It would create subtle directional differences in the way light arrives from the early universe. It would also bias the large-scale structure, making one direction statistically distinct from another. A rotating universe would carry a faint but persistent fingerprint. Observations push this further. The cosmic microwave background is remarkably uniform, with only small fluctuations. Those tiny variations are precious, because they encode conditions from the early universe. If the entire universe had a significant global rotation, it would imprint patterns in that background. It would also distort the distribution of galaxies in a directional way. The constraints suggest any overall rotation must be extremely small, if it exists at all. So we face an unsettling puzzle that sits right at the intersection of everyday experience and cosmic measurement. Local systems spin up easily, and they do it everywhere we look. Planets rotate, stars rotate, galaxies rotate, and clusters show hints of coherent motion. Yet the universe as a whole seems to keep its total angular momentum near zero, as if every twist is balanced by a counter-twist. That balance could be an accident of initial conditions, a cosmic coin flip that happened to land near zero. It could be a consequence of deeper symmetries in cosmology, where the simplest large-scale solutions have no preferred direction. It could reflect the way inflation stretched space and diluted any primordial rotation. Or it could point to something we have not fully understood about what angular momentum really is. Even in familiar settings, conservation raises questions that do not go away just because the math works. If angular momentum cannot be created from nothing, then any spin we see must come from somewhere. A skater speeds up by moving arms inward, but the initial spin had to be started. A planet spins because its forming material carried angular momentum, and collisions redistributed it. A star spins because the cloud that formed it was not perfectly still. But then we ask the next question, which is harder to keep purely mechanical. Where did that initial angular momentum come from in the first place? In a young solar system, we can trace it to the motions of gas and dust, stirred by turbulence and shaped by gravity. In a galaxy, we can trace it to mergers, tidal torques, and gravitational interactions. In the early universe, we can trace motions back toward primordial fluctuations. At each step, the trail continues backward, and the conservation law keeps demanding a prior source. Gravity can amplify rotation by collapse, and interactions can shuffle angular momentum between parts, but the total remains. The rule does not tell us why there was a non-zero value to conserve. It tells us only that once it exists, it persists. Quantum spin makes the question sharper, not softer, because it refuses to be explained as mere motion of parts. Particles do not acquire spin by being spun up. They are born with it, and it comes in discrete amounts. Spin influences chemistry, magnetism, and the stability of matter. If spin is intrinsic, then angular momentum is not merely a property of moving stuff. It is a foundational feature of the world. That realization invites a quiet, unsettling thought. If angular momentum is tied to symmetry, then spin is tied to the universe's underlying rules. It is not just that things happen to rotate, it is that the laws permit, and in some sense require, a conserved rotational currency. When we look at a magnet, or a spectrum of light, we are seeing that currency in circulation. The smallest scales echo the largest. So Chapter 1 sets the frame. We live inside layered rotations that our senses smooth into stillness, because the brain is calibrated for change, not constant drift. We can name the speeds and the timescales, from just 670 km per hour at Earth's equator to 30 km per second around the Sun. We can place the Sun in its 220 km per second orbit around the Milky Way. We can mark the galaxy's slow turn over 200 to 250 million years. We can also name the principle that binds these motions together. Angular momentum is conserved because the laws of physics respect rotational symmetry. That conservation is one of our most precise tools, and it works across classical and quantum domains. It explains why shrinking radius increases rotation rate, and why systems resist changes to their spin. It also explains why rotation tends to survive chaos, emerging intact after collisions and collapses. Yet the same principle exposes the paradox at the heart of this documentary. Spin is everywhere locally, but the universe looks globally unspun. The cosmic ledger seems to sum to nearly zero. with no preferred axis written across the sky. Physics can track angular momentum with ruthless accuracy, but it cannot fully explain why the first twist existed. From here, the path forward is clear. We will follow angular momentum from simple demonstrations into the machinery of planets and stars. We will see how gravity, collisions, and tidal torques generate rotation without violating conservation. And we will return again and again to the origin question that still refuses to sit still. If the universe began with no preferred direction, how did so many rotating structures emerge anyway? Next, we begin with the rule itself, and with the symmetry that makes rotation a conserved currency of reality. Stand still for a moment, then remember Chapter 1. Stillness is shared motion, and shared motion hides the deeper rule underneath. The universe does not merely move, it keeps accounts, and the accounts almost never fail. Picture a dark room with a single desk lamp. On the desk sits a ledger book, its pages ruled into neat columns. Every collision, every orbit, every swirl of air writes a line in that book, quietly, relentlessly, whether anyone is watching or not. Even when motion looks chaotic, the totals tend to come out clean. Physics has many conserved quantities, but three shape nearly every story about motion. Energy tracks the capacity to do work and to change states, whether that work is lifting a weight or breaking a chemical bond. Linear momentum tracks motion through space in a straight line sense, with both magnitude and direction. Angular momentum tracks motion around an axis, whether the axis is visible, shifting, or only defined by a choice of origin. These are not arbitrary human inventions, and they are not just clever shortcuts. Conservation laws are nature's refusal to lose information about certain totals, even as the details churn and rearrange. In an isolated system, you can trade forms and redistribute parts, but the ledger stays balanced. When the ledger seems to break, it usually means something external was ignored. Heat leaking out, friction with the environment, or a force from beyond the boundary. Energy conservation is the most familiar, and it is also the most easily misunderstood. Energy can move between kinetic, thermal, chemical, electrical, and gravitational forms without vanishing. Friction does not destroy energy. It converts organized motion into microscopic motion, where trillions of particles jiggle in directions too small to see. The total remains, even when it becomes hard to use, because low-grade heat is real energy, yet it is stubbornly difficult to turn back into focused motion. In visuals, this is where a sliding block becomes a thermal camera image. The block slows, but the surface warms in a faint spreading blush. The motion did not disappear. It dissolved into the restless vibration of atoms, and the ledger still adds up. Linear momentum is the simplest picture, because it points in a direction. A moving object resists changes to its motion, unless a net external force acts, and that resistance is what we call inertia. Collisions shuffle momentum between bodies, and the center of mass keeps its steady story even when parts ricochet wildly. Rockets work by throwing momentum backward in exhaust so the vehicle gains momentum forward, and the emptiness of space does not weaken that rule. If you could freeze a rocket plume in mid-air, you would see the accounting in geometry. A narrow, fast jet of gas carries as much momentum as a heavier, slower stream, and the rocket's acceleration is the reaction to that expelled motion. The engine is not pushing on space, it is balancing a book. Angular momentum is the third pillar, and it is the one that makes rotation feel inevitable. It is the conserved quantity associated with turning, orbiting, and spinning, and it appears whenever motion has a sideways component relative to an axis. It can be carried by rotating solids, by circulating fluids, and by bodies in orbit. It can also be carried by fields and by quantum particles, where the word spin stops being a metaphor and becomes a property of state. In everyday language, angular momentum sounds like a fancy name for spinning speed. In physics, it is more like a weighted measure of rotation, because distance from the axis matters as much as speed. Mass farther from an axis counts more, because it has a longer lever arm and contributes more strongly to the total. This is why changing shape can change spin rate without changing the total, and it is why a collapsing cloud can turn a barely detectable twist into a fast rotation. You can see this weighting in a simple visual. A figure skater extends their arms and the spin slows to a dignified turn. The arms come in close. Suddenly the rotation sharpens and the same person becomes a blur. The skater did not summon new angular momentum. They changed how the existing amount is distributed. So the opening claim is simple. Conservation laws are the universe's accounting system, and angular momentum is the account that tracks rotation. If you want to know why so much spins, you start by learning what cannot change. Once that constraint is in place, the rest of the story becomes a series of clever rearrangements rather than magical creations. The deeper reason conservation exists is not bookkeeping, but symmetry. A symmetry is a transformation that leaves the laws unchanged, even if the scene looks different. If you do the same experiment tomorrow and the rules are the same, that is a symmetry in time. If you do it here or across the room and the rules are the same, that is a symmetry in space. These sound like philosophical claims, yet they are testable in practice. Laboratories compare clocks, compare atomic transitions, and compare the behavior of particles under controlled conditions. The remarkable fact is not that the universe follows rules, but that the rules appear to be consistent across place and time to extraordinary precision. Rotational symmetry is the idea that the laws do not care which way you face. Turn your apparatus by 10 degrees, or 90, or any angle, and the fundamental outcomes are governed by the same equations. The universe does not label one direction as special in ordinary space, and that indifference has consequences as strict as any rule we know. If the laws truly have no preferred orientation, then something about rotation must remain invariant. Emmy Noether proved the modern version of this connection in the early 20th century, during a period when physics was being rebuilt from the ground up. Working in an era when women were often barred from formal positions, she developed mathematics that quietly reshaped theoretical physics. Her theorem says that every continuous symmetry corresponds to a conserved quantity. Time translation symmetry gives energy conservation. Space translation symmetry gives linear momentum conservation. Rotational symmetry gives angular momentum conservation. Noether's theorem can sound like pure mathematics, but its plain meaning is physical. If the rules do not change under a smooth shift, then there is a quantity that cannot change during motion. Symmetry is the reason the ledger exists. Conservation is the shadow that symmetry casts on events. A useful way to picture this is to imagine sliding the entire experiment through time or rotating it in space. If the underlying equations do not notice, then the outcomes must contain an invariant, sum total that refuses to drift. The conserved quantity is not an added rule on top of physics. It is what physics looks like when the laws are indifferent to a transformation. This is why angular momentum conservation feels so unbreakable. It is not enforced by a particular force, and it is not a special feature of gravity. It is enforced by the structure of the laws themselves, as long as space has no preferred direction. When we see angular momentum persist, we are seeing symmetry persist. To make this intuition usable, physics gives rotation its own version of force. Force changes linear momentum, and torque changes angular momentum. Torque is what you get when a force acts with a lever arm, and the lever arm is the perpendicular distance to the axis. Push on a door near the hinges and it barely turns. Push near the handle and it swings easily because the torque is larger. In a clean diagram, the same force arrow produces different results depending on where it is applied. The hinge becomes a pivot, the handle becomes a multiplier, and the door becomes a lesson in geometry. Rotation is not only about how hard you push, it is about where the push has room to twist. The math can be light and still be accurate in spirit. Angular momentum changes only when there is a net external torque. If the net external torque is zero, angular momentum stays constant, even if the object's rotation rate changes as its shape changes. That is the rotational version of Newton's first law, and it is as unforgiving as inertia in a straight line. This is why a spinning wheel resists being tipped, and why gyroscopes seem stubborn. The wheel's angular momentum points along its axis, and changing that direction requires torque. If you apply a torque, the response can be sideways, because rotation has its own geometry and its own vector rules. The details can wait, but the rule cannot. Turning a spinning axis is not like pushing a sliding block. A bicycle wheel held by its axle makes the point vivid. The wheel spins, your hands try to tilt it, and the wheel answers with a strange sideways insistence. That insistence is not personality. It is conservation, expressed through the way angular momentum vectors must change. In real life, torques are everywhere, so conservation is never perfectly isolated. Friction applies torque and slowly drains rotational energy into heat, even while the angular momentum may persist until something external grabs it. Tidal forces apply torque and move angular momentum between bodies, reshaping orbits and spin rates over long timescales. Collisions apply torque and redistribute spin among parts, sometimes turning orderly rotation into tumbling chaos. Still, the accounting remains powerful because the transfers are trackable. Angular momentum can move from orbit into spin or from spin into orbit, and the exchange can be measured. It can move from one object to another through contact forces, gravitational interactions, or magnetic coupling in plasmas. It can also be carried away by radiation, like light leaving a system, because light can carry angular momentum too. The total changes only if something external carries it away. This is the point where the documentary's hook becomes a rule. Nearly everything spins because once angular momentum exists, it is hard to erase. Systems can dissipate energy easily, but they cannot dissipate angular momentum without a torque channel that exports it elsewhere. Nature can smooth motion into heat, but it cannot smooth rotation into nothing without an exchange. What looks like spin dying out is usually spin being handed off. Now we add a second layer that changes how this feels. Conservation laws are easiest in inertial frames, where Newton's laws take their simplest form and the bookkeeping is clean. An inertial frame is one that is not accelerating or rotating, so a free object moves in a straight line at constant speed. In that frame, forces are real interactions, and the equations do not need extra terms to compensate for the observer's motion. But we live on a rotating planet, and we often describe motion in a rotating frame. A rotating frame is not inertial, because it is accelerating even if its rotation rate is constant. In a rotating frame, objects appear to curve even when no real force is acting on them. To keep Newton's equations useful, we introduce fictitious forces, and the word fictitious is more subtle than it sounds. Fictitious does not mean imaginary in their effects. It means they arise from the choice of frame, not from a physical interaction like gravity or electromagnetism. The centrifugal effect appears to push objects outward in a rotating frame, as if something is tugging them away from the axis. The Coriolis effect appears to deflect moving objects sideways relative to the rotation, bending paths into arcs that can look like intentional turns. A simple visual makes the point. From above a spinning turntable, a ball rolled straight across traces a line in the room, but a curve on the turntable. The ball did not change its mind. The coordinate grid did. On Earth, these effects are not small curiosities. They are part of the planet's large-scale behaviour. Air moving from high pressure to low pressure does not travel in a straight line across the map. It curves because Earth rotates beneath it, and the rotating frame changes the apparent path. The result is organised patterns that would not exist on a non-rotating world, and the patterns are so consistent that sailors and pilots have relied on them for centuries. The Coriolis effect helps shape trade winds, jet streams, and the spin of storms. It does not create motion from nothing, but it redirects motion that already exists, and that redirection matters when distances are large. Hurricanes rotate because pressure gradients drive inflow toward a low-pressure core, and Earth's rotation deflects that flow. The storm becomes a rotating system, and then angular momentum conservation shapes its structure. Tightening winds as air spirals inward, much like the skater pulling in their arms. In satellite imagery, the atmosphere looks like a living fluid sculpture. Cloud bands curl in sweeping commas, and the eye of a storm opens like a calm pupil inside a spinning iris. The rotation is not decoration. It is the signature of a planet that turns beneath its own weather. The centrifugal effect also shows up in subtle ways. Earth is slightly flattened at the poles and bulged at the equator, because rotation changes the effective balance between gravity and the outward tendency in the rotating frame. The oceans and atmosphere respond to that effective outward influence, settling into shapes that reflect a rotating equilibrium. Even the value of gravity you measure depends slightly on latitude, because rotation changes the effective acceleration, and because Earth's radius changes with location. These frame effects matter for our story, because they connect local rotation to global context. We do not just observe spin from the outside. We live inside a rotating coordinate system that constantly rewrites how motion looks, and that rewriting can hide or reveal the underlying conservation. Understanding spin everywhere requires knowing what is real torque and what is frame bookkeeping. This is also where angular momentum becomes a practical diagnostic. In an inertial frame, you can track angular momentum and predict how systems evolve. because the conservation statement is direct. In a rotating frame, you can still track it, but you must account for apparent forces and the torques they imply in the chosen coordinates. The physics does not change, but the description gains extra terms, and those terms can be mistaken for new causes. Those extra terms are the price of riding a spinning planet. With that foundation, we can climb back outward to cosmic scales. Gravity does not directly create angular momentum, because gravity is a central force in simple two-body form. A central force points along the line between bodies, so it produces no torque about that line, and that is a geometric fact. If a system begins with exactly zero angular momentum and perfect symmetry, gravity alone will not invent a net spin. Yet the universe is not built from perfect symmetries. Real clouds are lumpy, and real environments are noisy, with random motions layered on top of overall collapse. Tiny asymmetries are everywhere, from density fluctuations to small sideways velocities and uneven inflows. When gravity pulls matter inward, those small irregularities matter because collapse amplifies what was already present rather than averaging it away. The key amplification is geometric and relentless. Angular momentum depends on both sideways motion and distance from the axis, so radius is a lever that can be shortened dramatically. If a rotating cloud contracts, its moment of inertia drops, sometimes by enormous factors. With little external torque, the angular momentum stays nearly constant, so the rotation rate rises, often by orders of magnitude. What begins as a slow drift becomes a rapid spin simply because the same total is now packed into a smaller shape. This is the same logic as the skater pulling in their arms, but written on a cosmic stage. A diffuse cloud can rotate imperceptibly and still carry a non-zero angular momentum, because even a tiny sideways speed counts when the radius is vast. As it collapses into a star and a disk, the same angular momentum becomes dominant. The cloud's slight twist becomes a fast spin and a flattened structure, because rotation resists collapse most strongly in the direction perpendicular to the axis. In star formation, this is not a detail, it is architecture. Collapsing gas tends to form a rotating disk, because material with higher angular momentum cannot fall straight in without shedding that angular momentum first. It piles up in orbit, and friction within the gas and magnetic effects in ionized material help redistribute angular momentum outward. The inner regions can then fall further, while the outer regions take up the excess, and the system naturally separates into a central object and a disk. In a telescope's view, these disks are not abstract. They glow in infrared, traced by dust warmed by newborn starlight, and they show lanes, rings, and gaps that hint at forming planets. The disk is angular momentum made visible, matter taking the only stable shape available when it cannot simply drop straight inward. Planets form in that disk, inheriting a portion of the original rotational budget. Some of their spin comes from the local swirl of the disk, and some comes from impacts that add or subtract angular momentum, like abrupt deposits and withdrawals. Even the tilt of a planet's axis can be read as a history of torques, gentle, persistent ones from the disk, and violent, sudden ones from collisions. In galaxy formation, the story repeats with different actors. Protogalactic gas and dark matter do not collapse in isolation, because the early universe is a crowded landscape of growing structures. Tidal torques from neighbouring overdensities twist the forming halo, and those torques arise because the mass distribution is never perfectly spherical. Small gravitational pulls from nearby structures act like long lever arms, gradually turning a forming system as it collapses. The net angular momentum can remain modest in absolute terms, but collapse turns modest into visible rotation. A galaxy can begin as a region only slightly biased in its motions, yet end as a rotating disk tens of thousands of light-years wide. When you see a spiral galaxy, you're seeing a conserved quantity expressed at scale, with stars and gas tracing out the long memory of earlier symmetries. Mergers add another route to spin without violating conservation. Two galaxies approach with orbital angular momentum, and their interaction transfers some of it into internal rotation through gravitational torques and dynamical friction. Tidal tails fling stars outward like streamers, carrying angular momentum into extended arcs. The remnant can spin, or it can become more random in motion, depending on geometry and gas content, but the total is not lost. It is redistributed into new patterns. This is why rotation is so common in astronomical objects. Collapse concentrates angular momentum and interactions shuffle it into new forms, sometimes from orderly orbits into internal spin. Even if initial spins are tiny, the universe has many ways to preserve and amplify them. The important point is that none of these processes creates angular momentum from nothing. They only move it around and change how it is expressed. Now the tension enters. Conservation laws tell us what cannot change, but they do not tell us what the initial values were. A conserved quantity must be conserved from some starting point, and that starting point matters. If the starting point is unknown, conservation becomes a constraint, not an origin story, and constraints can be sharp without being satisfying. In the early universe, we can describe conditions with extraordinary success using a small set of parameters. We can track expansion, composition, and the growth of structure from tiny fluctuations. We can map the cosmic microwave background as a snapshot of the universe when it was young, when matter and radiation last scattered freely. We can test whether the universe has a preferred direction, and the answer appears to be no within tight limits, as if space itself refuses to pick a favoured axis. That near isotropy suggests that the universe's total angular momentum is close to zero. If there were a large global spin, it would likely imprint a directional pattern in the microwave background, like a faint smear or alignment across the sky. It would also introduce anisotropies in large-scale structure that would be hard to hide, because a rotating universe would subtly bias how matter collapses. Observations do not favour a universe with a strong overall rotation, and that absence is itself a clue. So the central question sharpens rather than fades. If the total is near zero, why is angular momentum so abundant locally? How can galaxies, stars, and planets spin so readily, while the cosmos as a whole shows no preferred axis? How does a universe with no global twist produce so many local whirlpools, each with its own direction and history? One answer is that zero total does not mean zero everywhere. A system can have parts with equal and opposite angular momentum that sum to zero, and the cancellation can be exact even when the parts are dramatic. Two skaters can spin in opposite directions with equal magnitude, and the total is zero. A pair of galaxies can orbit with opposite contributions relative to a chosen origin, and the total can cancel even while both are moving intensely. In the early universe, random fluctuations can generate local vorticity and local angular momentum while keeping the global sum near zero. Regions can acquire spins in different directions through tidal torques and interactions, and neighbouring patches can end up counter-rotating. The universe can remain globally unbiased while becoming locally rotational. Balance does not require stillness, it requires cancellation, and cancellation can hide enormous activity. But this shifts the mystery rather than ending it. Cancellation explains how the total can be near zero today, and it explains how opposite spins can coexist. It does not fully explain why the distribution of angular momentum emerged the way it did, or why certain scales ended up with the spins we observe. It does not explain why the universe's initial conditions allowed rotational degrees of freedom to populate structures so effectively, rather than washing out into purely radial collapse. We can push the question back to the earliest moments we can model. After the Big Bang, the universe expanded and cooled, and small density variations grew into the cosmic web of filaments and voids. Those variations are measured, and their statistics are close to uniform in direction, as if the early universe had no reason to prefer one orientation over another. If angular momentum is conserved, then any net rotation must trace back to those beginnings. So what set the initial angular momentum distribution, and what decided how much would be available for later amplification? This is the origin problem in its cleanest form. Conservation laws are powerful, but they are not creative. They preserve what exists and they constrain what can happen next, sometimes with astonishing precision. They do not tell you why the initial ledger was filled with these numbers rather than others. They do not tell you why the universe began with the capacity for rotation at all, instead of a state with no angular momentum anywhere. At this point, classical intuition starts to run out of room. In classical mechanics, angular momentum is built from mass moving through space, and you can picture it as distance times sideways motion. You can imagine it being transferred by pushes and pulls, by collisions and gravitational tugs. You can always ask what started the motion, and you can always look for the earlier torque. Quantum mechanics changes the terms of the discussion, and it does so in a way that feels almost confrontational. Particles carry angular momentum, even when they are not orbiting anything, and even when there is no extended object to spin up. This is spin in the strict sense, and it is not optional. Electrons, protons, neutrons, and many other particles come with intrinsic angular momentum built in as a defining feature of what they are. They do not need to be spun up, and they do not slow down through friction, because intrinsic spin is not a tiny ball rotating in space. Quantum spin also comes in discrete units, not a continuous range. You can measure components of spin, and the outcomes are quantized, landing on specific allowed values rather than any number in between. The rules are probabilistic, but the conservation is exact in the right contexts, and it governs what reactions can occur. When particles interact, their spins can flip, combine, and entangle, but the total angular momentum is still conserved, with orbital and intrinsic parts contributing together. This makes Noether's insight feel even deeper. Rotational symmetry does not just protect the spin of wheels and planets, or the orbits of moons and satellites. It protects a conserved quantity that exists even when there is nothing literally rotating in space, and that is a profound shift. Angular momentum becomes a fundamental label of states, not merely a derived property of motion. In quantum language, it is part of the bookkeeping that defines what outcomes are even possible. In other words, rotation is not just something matter does. Rotation is something the laws keep track of at the most basic level, even when our mental pictures struggle. The same conserved currency appears in atoms, in magnets, in light, and in galaxies, linking the very small to the very large. The universe seems built to count angular momentum, even when the thing carrying it is not a spinning object in any ordinary sense. We can now restate the chapter's core foundation in one line. Conservation laws exist because symmetries exist, and angular momentum exists because space has no preferred direction. That explains why spin persists and why collapse amplifies it, and it explains why torque is the only honest way to change the total. It does not yet explain why the universe had non-zero angular momentum in its parts to begin with, or why intrinsic spin is written into matter at all. That gap is the narrative hinge for the rest of the series. Classical physics tells us how angular momentum moves and concentrates, and it gives us the tools to track transfers across systems. Cosmology tells us the universe is globally close to directionless, with totals that nearly cancel and with no obvious cosmic axis. Quantum mechanics tells us angular momentum is intrinsic, quantized, and unavoidable, and that it shapes the identity of particles as surely as mass and charge do. The mystery is not whether spin is conserved. The mystery is why spin is so deeply written into reality, and why the universe's earliest conditions allowed this conserved quantity to be expressed everywhere. When you watch a storm tighten, a planet rotate, or a galaxy turn, you are seeing a rule that never breaks, and you are also seeing a question that refuses to go away. The next step is to go smaller than atoms, where the word spin stops being metaphor and becomes a strict quantum number. We will follow angular momentum into quantum rules, where particles carry it as identity, and where measurement itself has structure. We will see how intrinsic spin shapes matter, forces, and the stability of the world, and we will return to the cosmic balance with sharper tools. We will keep asking how a universe with no preferred direction can still be built from spinning parts. To understand spin everywhere, we must go smaller than atoms, into quantum mechanics, where spin is not optional but fundamental. Stand still for a moment, then remember the twist from Chapter 2. Angular momentum is conserved because space has no preferred direction, and the laws of physics do not change when you rotate your coordinate system. That symmetry sounds abstract, yet it operates with relentless consistency, from planets and galaxies down to the smallest excitations of quantum fields. The rule does not fade as we zoom inward, because the symmetry is built into space itself rather than into any particular object. It continues downward until rotation becomes a quantum number, and until angular momentum becomes something a particle simply is. So the opening claim is simple. Quantum spin is intrinsic angular momentum carried by particles, even when nothing is literally rotating in the everyday mechanical sense. Electrons, protons, neutrons, and many atomic nuclei carry spin as part of identity, like mass and electric charge. In the standard model's language, spin is one of the labels that tells you what kind of field excitation you are dealing with. Photons also carry angular momentum, including polarization-related spin and orbital components, when light is structured into twisted wavefronts. In the quantum world, angular momentum is not only about objects turning, it is also about how states respond when the universe is rotated around them. In quantum mechanics, spin is not a continuous dial you can turn smoothly, as if you were adjusting a knob on a machine. Spin comes in quantized values fixed by the particle's type, and those values are measured in units set by Planck's constant. More precisely, the magnitude is tied to subpuls 1 kd, while measurements reveal discrete projections in steps of h. An electron has spin 1/2, meaning measurements return discrete outcomes rather than a continuum of possible projections. A photon has spin 1, tied to the two helicity states that survive in free space because the photon has no rest frame. The numbers sound like bookkeeping, yet they encode deep geometric facts about how nature represents rotations. The word spin invites a wrong picture, and the wrong picture is stubborn. It suggests a tiny sphere turning like a top, with a definable surface and a definable angular speed. But many particles behave as point-like down to the smallest distances we can probe, with no measurable size to spin in the classical sense. In high-energy scattering, the electron keeps refusing to reveal any internal radius, even as we push to shorter wavelengths. They still carry spin, and they still obey angular momentum conservation with the same strictness as a rotating planet. The name is historical, and the intuition it tempts us toward is exactly what quantum theory had to outgrow. If an electron were a classical spinning ball, its surface would need to move faster than light to produce the measured magnetic effects. That contradiction is more than a curiosity. It is a warning that the analogy breaks at the foundation. Spin is not a literal rotation of extended matter, and it is not a hidden mechanical motion waiting to be discovered. Instead, the magnetic moment is tied to spin through a proportionality factor, and for the electron that factor is slightly corrected by quantum fluctuations. Spin is a property of the quantum state, revealed through measurement and interaction, and encoded in how the state transforms under rotations. In plain terms, it is angular momentum without a spinning object. The first decisive evidence came from a beam of atoms and a magnetic field, in an era when quantum theory was still being assembled from clues. In 1922, Otto Stern and Walter Gerlach sent silver atoms through a non-uniform magnetic field, using a carefully heated oven to create a narrow atomic beam. The apparatus was almost artisanal: hot metal, collimating slits, and a magnet shaped to produce a steep gradient. Classical physics predicted a smear of deflections because a magnetic moment could point at any angle and would be pulled by varying amounts. The actual beam split into discrete parts, as if nature allowed only certain orientations when the atoms met the field gradient. The visual is almost too clean to be real: one beam entering, two separated traces emerging, like a fork in reality itself. That split was not a technical artifact, and it was not a quirk of silver chemistry. It was quantization made visible, stamped onto a photographic plate as separate bands rather than a continuous blur. The atoms carried angular momentum that could only project into specific values along the measurement axis set by the apparatus. In modern terms, the magnetic field gradient couples to the component of the magnetic moment along the field direction, turning spin information into spatial separation. The magnet did not merely reveal a hidden direction that was already there in a classical sense. It forced a quantum choice among allowed outcomes, and it did so repeatedly, atom by atom, with statistics that could be counted. Silver was a clever choice because one electron dominates its magnetic behavior, which makes the interpretation unusually direct. The atom's net magnetic moment mostly reflects an unpaired electron in its outer shell, while the other electrons pair off and cancel. The discrete splitting therefore pointed to electron spin, even before the full theory of spin and relativistic quantum mechanics was settled. Historically, this arrived as the Bohr, Sommerfeld picture was straining under new data, and as wave mechanics and matrix mechanics were about to reshape the field. A few years later, Uhlenbeck and Goudsmit proposed electron spin explicitly, and the idea first sounded like an audacious patch. The experiment turned an abstract quantum rule into a countable result, and it did so with a simplicity that still feels modern. Quantization is the core idea behind spin states, and it is also the reason spin is so useful as a concept. A spin state is not a tiny arrow fixed in space, as if the particle carried a miniature compass needle inside it. It is a set of probabilities for outcomes when you measure along a chosen axis, and those probabilities are what the theory predicts and experiments confirm. Change the axis, and you change the probabilities, even for the same prepared particle. because the measurement is not just reading a pre-written label. The axis you choose is part of the question you ask the universe, and the answer comes back in discrete syllables. This is where quantum mechanics breaks classical intuition cleanly, and it does so with mathematical precision. In classical rotation, you can know all components of angular momentum at once, limited only by how well you measure. In quantum spin, different components do not commute, so they cannot be simultaneously sharp in the same state. You can measure one component precisely, and the others become uncertain in a structured way that is not mere ignorance. The uncertainty is built into the geometry of the theory, like trying to pin down north, east, and up with a tool that can only lock one direction at a time. The mathematics packages this into operators and eigenvalues, and the language can sound forbidding at first, yet the physical meaning is direct. Spin has magnitude and direction-like behavior, but it does not behave like a classical vector you can fully specify. For spin 1/2, there are only two eigenvalues along any axis, and the state lives in a two-dimensional complex space rather than ordinary three-dimensional space. Measurement outcomes are discrete, and the act of measuring matters because it selects an eigenstate of the chosen component. In the lab, this selection is not mystical. It is an interaction with a magnetic field, a detector, and an environment that amplifies a microscopic difference into a macroscopic record. Now the tension enters. If spin is not literal rotation, why does it behave like angular momentum at all, and why does it obey the same conservation law? The answer is symmetry, the same theme that anchored Chapter 2, but now expressed in the language of quantum states. Quantum states transform under rotations, and those transformations come in families called representations, spin labels which family a particle belongs to, and that label determines what outcomes are possible when the world is turned around it. In other words, spin is how a particle fits into the rotational symmetry of space, the way a musical note fits into a scale. Rotations in quantum mechanics are not just turning an object in space, like spinning a chair in a room. They are transformations of the wave function, the object that encodes measurable probabilities for all possible outcomes. Under a full 360-degree rotation, many quantum states return to themselves, and for everyday objects that seems inevitable. A spin 1/2 state returns with a sign change, an overall phase of -1, which is physically meaningful when interference compares phases between paths. The state looks the same to a single measurement, yet it is not the same in a larger quantum context. Only after 720 degrees does the spinor come back exactly, a fact that feels like a riddle until you see the geometry behind it. That strange behavior is not a philosophical flourish, and it is not a trick of notation. It is measured in experiments that compare phases and interference patterns, including setups where particles take different routes and are recombined like waves. The sign change shows itself when you rotate a spinner and then interfere it with an unrotated reference, revealing a shift that cannot be explained by classical vectors. It is also built into the way particles combine their angular momentum, which is where the bookkeeping becomes predictive. Two spin 1/2 particles can add to total spin 0 or 1, and the allowed totals are quantized with strict rules. Those rules are not optional because they are enforced every time particles interact. When two spins combine, the composite system has a set of possible total angular momentum states, and the probabilities of each depend on how the pair was prepared. The singlet state is special because it has total spin 0, meaning the pair is rotationally symmetric as a whole. The triplet states have total spin 1, meaning the pair carries a net angular momentum that can point in discrete ways. Even before we discuss entanglement explicitly, the structure is already there. Nature is telling us that adding spins is not like adding arrows on paper. Spin is measurable because it couples to magnetism, and magnetism is one of the most sensitive amplifiers we have. A spinning charge in classical physics creates a magnetic moment, which is why a current loop behaves like a magnet. Quantum spin also produces a magnetic moment, even without a classical spinning charge distribution, and that moment interacts with external fields. Put a particle in a magnetic field, and its energy depends on spin orientation relative to the field direction. That dependence shows up as spectral lines and splitting patterns, because energy differences translate into photon frequencies. The simplest version is the Zeeman effect, where a single level becomes several, separated by a field tunable amount. In atomic spectra, this coupling is not a minor correction. It contributes to fine structure, hyperfine structure, and the detailed pattern of allowed transitions that give each element its characteristic fingerprint. The electron's spin couples to its orbital motion through spin, orbit interaction, which is partly a relativistic effect in the electron's frame. In plain language, the electron experiences an effective magnetic field due to its motion in the nucleus's electric field. The result is that energy levels split slightly, and those slight splittings are measurable with precision spectroscopy. When you look at a line that should be single and see it doubled or tripled, you're watching spin write itself into light. This is why spin matters inside atoms, where the architecture of matter is assembled. Electrons in atoms occupy quantum states labelled by quantum numbers, and those labels are not decorative. One quantum number describes orbital angular momentum, tied to the electron's spatial wave pattern and the shapes we call s, p, d, and f orbitals. Another describes intrinsic spin, which has only two projections for an electron along any chosen axis. Together they determine fine structure, selection rules, and how atoms absorb and emit light, which is why the colours of gases in a discharge tube are also a story about angular momentum. Even the darkness between spectral lines is information, because forbidden transitions are part of the pattern. The periodic table is not just chemistry's catalogue, and it is not merely an empirical list discovered by sorting substances. It is a map of allowed electron states, organised by how quantum numbers fill in order of increasing energy. Electrons fill shells and subshells according to energy and quantum constraints, and those constraints are strict. Spin is part of the counting, because each spatial orbital can host two electrons with opposite spin projections. That simple rule shapes the entire architecture of matter, from why oxygen is reactive to why noble gases are stable. It also explains why the table has its repeating periods, because the capacity of each shell is set by angular momentum and spin. The rule has a name because it is so fundamental, and because it explains stability that would otherwise be mysterious. The Pauli exclusion principle says no two identical fermions can share the same quantum state, meaning they cannot match in all quantum numbers at once. Electrons are fermions with spin 1/2, and their combined wave function must be antisymmetric under exchange of two particles. That antisymmetry is not a preference or a force. It is a structural requirement of quantum theory for identical half-integer spin particles, and it is mirrored in the way integer spin bosons behave oppositely. Without exclusion, electrons would all sink into the lowest energy state, crowding into the same orbital as if the universe allowed infinite occupancy. Atoms would shrink drastically, because nothing would prevent electrons from piling into the smallest, deepest state near the nucleus. Chemistry would lose its diversity, because bonding relies on the availability of distinct electron states, with distinct energies and spatial patterns. The world would be denser, simpler, and likely incompatible with complex structures like long molecules and stable solids. The familiar size of atoms is not guaranteed by electromagnetism alone. It is protected by spin-based statistics. In a sense, ordinary matter has volume, because quantum identity refuses to overlap perfectly. Exclusion is not a chemical convenience, and it is not a rule invented to fit data after the fact. It is a quantum consequence of spin and statistics, linking a particle's intrinsic angular momentum to how collections of those particles behave. Bosons with integer spin can pile into the same state, which enables lasers, Bose, Einstein condensates, and superfluidity under the right conditions. Fermions with half-integer spin resist crowding, which builds the stiffness of electron shells and the layered structure of atoms. Stability is a spin story, written into the permitted symmetry of many particle wave functions. It is also why matter can be both compressible and stubborn, yielding only so far before quantum rules push back. This stability reaches beyond atoms into bulk matter, where the same principle becomes a pressure you can calculate. Electron degeneracy pressure in dense systems arises from exclusion, because compressing electrons forces them into higher momentum states when lower ones are already occupied. It is not thermal pressure from heat, and it does not vanish when temperature drops toward absolute zero. It is a quantum pressure from the impossibility of compressing fermions into identical states, and it can be enormous. That pressure will matter later when gravity tries to crush stars, because gravity does not negotiate with chemistry, it only pulls. The fact that a cold object can still resist compression is one of quantum theory's most counterintuitive gifts. But before gravity takes over, spin already shapes the macroscopic world through magnetism, which is where quantum effects become visible at human scales. In many materials, electron spins pair up and cancel, leaving little net magnetic moment, even though each electron still carries spin. In others, interactions favour alignment, producing ferromagnetism that can lift paper clips and hold notes to a refrigerator. The difference comes from quantum exchange forces, not from tiny bar magnets acting classically. The electrons are not choosing to align out of preference. They are minimizing energy under the constraints of anti-symmetry. What looks like a simple togetherness is actually a many-body quantum compromise. A ferromagnet is a large-scale organization of microscopic spins, and the organization is rarely uniform across the whole object. Spins align in regions called domains, where many moments point the same way and reinforce one another. Domains form because alignment lowers energy locally, while domain walls reduce external field energy by limiting the magnetic field that leaks into surrounding space. The magnet you hold is a compromise between competing energy costs, a patchwork of order separated by thin boundaries where spins rotate gradually. If we could zoom in, we would see a landscape of aligned regions like continents on a map. Under a microscope sensitive to magnetic structure, the boundaries would look like living coastlines, shifting with stress and temperature. When you magnetize a piece of iron, you're not creating spin, and you're not injecting magnetism from outside. You're reorienting domains so more spins point together, often by moving domain walls and allowing one orientation to grow at the expense of another. The net field grows because cancellations shrink, and the object's external field becomes stronger and more coherent. Heat can scramble that order because thermal agitation competes with alignment and can break the delicate balance. Cooling can restore order because quantum interactions regain control and the lowest energy arrangement dominates. The Curie temperature marks the tipping point where disorder wins and the large-scale magnet seems to vanish. This is angular momentum showing up as a field you can feel, which is why magnetism has always seemed slightly uncanny. A compass needle turns because many electron spins in Earth's materials contribute to a global magnetic environment, and because the needle itself is a domain-structured ferromagnet seeking alignment. In technology, spin alignment can lock in memory states, which becomes data storage and sensing. The microscopic conserved quantity becomes macroscopic behavior, bridging the invisible quantum world and the tactile world of forces and motion. What looks like a simple attraction is actually a collective quantum arrangement persisting against disorder. It raises a quiet question. How much of the everyday world is solid only because quantum numbers refuse to share? Spin also appears in light, which carries angular momentum without mass and without rest. Circularly polarized photons carry spin-angular momentum tied to handedness, meaning the electric field rotates as the wave propagates. Light can transfer angular momentum to matter, exerting torque on small particles, especially when the particles are trapped in focused beams. Optical tweezers can trap and rotate microscopic objects using photon angular momentum, turning light into a tool that can twist the material world. In a darkened lab, you can watch a tiny object spin because the field's angular momentum must go somewhere. Even the emptiness between source and target is not empty, because the electromagnetic field carries the conserved quantity through space. Now we return to the documentary's central question from a new angle, and the angle is conservation. If angular momentum is conserved, then spin must balance in interactions, even when particles appear and disappear in reactions. In quantum processes, particles are created and destroyed, yet total angular momentum is still conserved across the entire interaction. The balance can be shared between intrinsic spin and orbital motion, and it can also be carried away by emitted photons. The ledger remains, even when the actors change, because symmetry does not care which cast is on stage. Conservation is less like a rule of thumb and more like an accounting identity that cannot be violated. This balance becomes most striking in entanglement, where conservation is enforced through a shared state rather than through classical coordination. When two particles are produced together, their total spin can be fixed by the creation process, such as the decay of a parent particle with known angular momentum. A common case is the singlet state, where two spin one-half particles have total spin zero, meaning the pair carries no net angular momentum. Neither particle has a definite spin direction by itself, even if we wish it did. The pair has a definite total, and that total is conserved with perfect accounting. It is as if the universe stores the certainty in the relationship, not in the individuals. Measure one particle's spin along an axis, and you get a random outcome because the singlet state does not privilege any direction. But the partner's outcome is constrained to keep the total consistent, and the constraint is exact. If one is found up along that axis, the other will be down along the same axis, even if the axis was chosen at the last moment. The correlations persist even when the particles are far apart, separated by meters, kilometers, or more. The conservation law reaches across separation through the shared quantum state, as if the pair remains one object in the only sense that matters to the mathematics. The unsettling part is not that the totals balance, but that the balance is real before any single direction is decided. Entanglement does not allow faster-than-light signals, and it does not let you choose the outcome on one side to control the other. The randomness remains, and only the correlations are fixed, which preserves causality and prevents communication through mere measurement. But it does show that the universe enforces angular momentum accounting in a non-classical way, without hidden gears turning in the background. The balance is not carried by a secret spinning mechanism or by a message sent between particles. It is carried by the structure of the joint state, which encodes what can be true together. We are forced to ask what property even means when the property belongs to the pair. Experiments have tested these correlations with increasing rigor, closing loopholes that once allowed skeptics to imagine classical explanations. They violate classical assumptions about local hidden variables under reasonable conditions, meaning no theory that keeps both locality and predetermined outcomes can match the data. The result is not that conservation fails, and it is not that physics becomes arbitrary. The result is that our classical picture of separate properties fails, because the properties are not always locally owned before measurement. Spin remains measurable and conserved, but it is not always an individual possession in the way classical intuition demands. This is the chapter's conceptual pivot, and it deserves to be held in mind as we move forward. Spin is angular momentum that is not made of rotating parts, yet it behaves with the same seriousness as any conserved quantity. It is quantized, conserved, and deeply tied to symmetry, which is why it appears wherever rotations matter. It shapes matter's stability through exclusion and degeneracy, preventing collapse into a featureless heap. It shapes macroscopic fields through collective alignment, turning microscopic quantum numbers into forces we can engineer. It links distant particles through entanglement while preserving total balance, revealing that conservation can be global even when properties are not local. Now we connect the abstract to the everyday, because spin physics is not trapped in textbooks and chalkboards. MRI uses nuclear spin in hydrogen atoms to map the body, relying on the fact that protons behave like tiny magnetic dipoles due to their intrinsic angular momentum. A strong magnetic field aligns those spins slightly, producing a small excess of spins pointing with the field. Radio pulses then tip the net magnetization away from alignment, and the spins precess like synchronized tops in a magnetic landscape. As spins relax back toward equilibrium, they emit signals that encode tissue environments, because different molecular surroundings change relaxation times in measurable ways. The image is built from those differences, turning quantum relaxation into clinical contrast. The visual here is almost cinematic, even though it happens invisibly inside a machine. A patient lies still while a powerful magnet establishes a silent order in the body's hydrogen nuclei. Coils transmit radio frequency pulses, and gradients in the magnetic field label position by changing precession frequency across space. The returning signals are faint, yet they can be reconstructed into detailed images because the spin dynamics are predictable and stable. The medical miracle is built on an intrinsic quantum number, translated into a map of soft tissue. In a very literal sense, the body is being read by listening to angular momentum settle back into balance. Atomic clocks also rely on quantum angular momentum, and their precision depends on how sharply nature defines certain spin-dependent energy differences. They count extremely stable transitions between hyperfine states, which depend on electron and nuclear spins interacting through magnetic coupling. The clock's tick is a spin-dependent energy difference, measured with microwaves and stabilized by feedback that locks an oscillator to the atomic transition. In practice, the clock is a conversation between electronics and quantum states, with the atom providing the unchanging reference. Modern navigation and communications depend on this stability, because timing errors become position errors at the speed of light. The more perfectly we control spin states, the more precisely we can anchor time itself. Quantum sensors push the same idea further, using spin as a probe of the environment rather than merely a label. Spin states can be exquisitely sensitive to magnetic fields, rotation, and acceleration, because tiny changes in field or motion shift quantum phases. Devices based on NV centers in diamond read out electron spin with light, turning a defect in a crystal into a nanoscale magnetometer. Cold atom interferometers use spin and phase to measure gravity gradients, converting quantum coherence into a measurement of the Earth's pull. The technology works because spin is a real conserved quantity, not a metaphor, and because its quantum evolution is coherent enough to track. The practical challenge is always the same. Keep the environment from scrambling the phase before the measurement is complete. Spin also constrains what reactions can happen, which is why it appears across disciplines that rarely share the same vocabulary. In particle physics, conservation of total angular momentum and parity shapes decay channels, determining which final states are allowed and which are suppressed. In chemistry, spin selection rules can slow reactions, creating long-lived excited states when a transition would require a forbidden spin flip. In astrophysics, polarized light reveals magnetic fields and scattering geometries, because polarization is a direct signature of photon angular momentum. Across fields, spin is a rule that narrows the possible histories, turning symmetry into prediction. So the opening claim is simple, now with weight behind it, and with evidence that spans a century of experiments. The universe does not merely contain rotating objects like planets, wheels, and storms. It contains angular momentum as an intrinsic label of matter and light, embedded in the quantum structure of reality. Even if the cosmos has no preferred direction overall, its smallest building blocks carry spin as a built-in currency. The conservation law does not merely track motion, it tracks identity. Now the tension enters again, sharper than before, because the idea has consequences that are easy to miss. If spin is intrinsic, then angular momentum is not only inherited from earlier motion, like a skater pulling in their arms. Some of it is present as a property of particles themselves, even in a perfectly still laboratory. Yet the universe still appears globally balanced, with no obvious net rotation written across the sky. The ledger seems to cancel across scales, from entangled pairs to cosmic structure, as if nature prefers totals that add to zero. Is that apparent calm a deep principle, or simply the outcome of countless balanced creations and cancellations? That cancellation does not mean spin is irrelevant, and it does not mean angular momentum is diluted into meaninglessness. It means spin is distributed in opposing ways, often created in balanced pairs to satisfy conservation from the start. In quantum fields, particles can be produced with opposite spins to keep totals fixed, like a perfectly balanced transaction. In atoms, electrons pair with opposite spins to lower energy and cancel magnetic moments, which is why so many substances are not magnetic. In bulk matter, domains can oppose and reduce external fields, hiding immense internal order behind an apparently quiet exterior. The universe can be full of spin and still look calm. Balance is a theme, not an ending, and it sets up the next escalation. The same conservation that keeps totals fixed also enables dramatic spin-ups when size shrinks, because angular momentum has to go somewhere as geometry changes. In classical systems, collapse turns small angular momentum into fast rotation, and we see it in everything from figure skaters to forming planets. In quantum systems, exclusion and degeneracy resist compression until gravity overwhelms them, storing stability like a spring under load. The next chapter will use that hinge, where the microscopic rules stop being gentle and start being decisive. Transition to Chapter 4. Quantum spin underpins stable matter, but gravity can compress matter until those quantum rules become engines rather than safeguards. When stars die, conservation laws turn collapse into a cosmic turbine, and the numbers become extreme. The fastest spins in the universe are born when quantum structure meets gravitational collapse, and when angular momentum that once seemed negligible is concentrated into a remnant only kilometers across. What began as a subtle sign, change in a wave function becomes, in the end, an object that can sweep a beam across space like a lighthouse. We started with the illusion of stillness, then learned the rule that never breaks. Now we have met the most counterintuitive form of angular momentum, carried by particles that are not spinning objects, yet still shaping everything they touch. The universe spins because symmetry allows angular momentum, and because conservation forces it to persist through every interaction. The next step is to watch gravity concentrate the conserved quantity into the most extreme rotators nature can make, where spin and collapse become inseparable parts of the same story. Stand still for a moment, then remember the rule that never breaks. Angular momentum persists, and gravity can concentrate it until rotation becomes extreme. In physics terms, the total angular momentum of an isolated system stays fixed unless an external torque intervenes. That statement sounds abstract, yet the night sky keeps demonstrating it with ruthless clarity. What looks like chaos in a telescope often hides a strict accounting. Motion cannot simply vanish. Even when energy is radiated away as light, the sideways spin budget must still be tracked. Stars begin with inheritance, not invention. They form inside molecular clouds that already drift, shear, and rotate slightly. These clouds are cold by everyday standards, often only tens of kelvins, so their gas moves slowly and can remain gravitationally bound. Much of the mass is molecular hydrogen, which is hard to see directly, so dust and trace molecules become our signposts. Carbon monoxide lines, for example, map the cloud's kinematics and reveal subtle velocity gradients that hint at rotation. Astronomers read those gradients through Doppler shifts, tiny changes in frequency that translate into kilometers per second. In wide-field images, the clouds look like smoke lit from within, filaments, knots, and dark lanes cutting across starlight. Against the Milky Way star fields, the densest parts appear as ink-black silhouettes, swallowing visible light and forcing us into infrared and radio. Turbulence adds random eddies across many scales, from subparsec swirls to flows spanning whole cloud complexes. Supersonic motions create shocks that compress gas into sheets and filaments, and those structures then fragment into cores. Nearby masses apply weak tidal torques, and the larger galaxy imposes shear through differential rotation. Even when the net spin is small, it is rarely exactly zero, because perfect cancellation is statistically unlikely. If you could freeze a cloud and draw arrows for every parcel's sideways motion, the pattern would look tangled, yet the sum would still lean one way. That faint preference, barely noticeable at first, becomes decisive once gravity starts shrinking the system. There is also a deeper reason small spins are hard to erase. In a turbulent cloud, parcels of gas collide and mix, but they do not instantly cancel each other's sideways motion. Shocks dissipate energy efficiently, turning bulk motion into heat that the cloud can radiate away. Angular momentum is harder to drain without a lever arm, because you must push on something at a distance to change it. The cloud can cool by radiating infrared light from dust grains, but it cannot radiate away rotation directly, so a faint inherited twist survives long enough to matter, and it can even become more coherent as collapse selects the densest regions. Magnetic fields complicate this survival story, because they can couple gas to its surroundings and apply braking. Yet even magnetic braking has limits, and it often leaves enough spin to build a disk. As a cloud collapses, rotation stops being a footnote. Angular momentum depends on sideways motion and lever arm, so large radii hide large totals. A slow drift at a huge distance can outweigh a fast motion close in, because the lever arm multiplies the effect. When gravity shrinks the lever arm, the same total demands a faster spin. The figure skater analogy is accurate, but the scale change is astronomical, and the consequences are far more violent. In the language of mechanics, the moment of inertia falls sharply as mass concentrates, and the rotation rate rises to compensate. What begins as a barely rotating cloud can end as an object whose surface moves at a significant fraction of light. Picture the visual progression as if the camera never blinks. A molecular cloud spans light years, and its rotation can take millions of years to complete a turn. The view glides along cold filaments where dust grains align with magnetic fields and polarize the faint glow. The camera then dives inward to a dense core, where dust blocks visible light and only infrared can see through. Inside, the temperature rises from tens of kelvins to hundreds, and the chemistry shifts as ices sublimate from grain surfaces. The core becomes a protostar, glowing faintly as gravitational energy turns into heat. The protostar may span only a few solar radii, and now rotation can be measured in days. Collapse continues, and the remnant can shrink to a size comparable to a city. At that point, rotation can reach milliseconds, so fast that the object's surface speed becomes a significant fraction of light. In a visualization, The scale bar keeps shrinking while the spin indicator accelerates until the numbers feel almost unreal. The numbers are not decoration, they are conservation made visible. A radius shrinking by a factor of 1,000,000 can, in principle, raise rotation rates by 1,000,000. In practice, angular momentum is redistributed and lost along the way, yet the trend remains unmistakable. The collapse is not a single plunge, but a sequence of stages where different forces take turns dominating. Every stage of collapse is a negotiation between what gravity wants and what rotation allows, and the terms of that negotiation are written into the final spin. When we measure a remnant's period, we are reading the final line of that contract. Collapse also reshapes geometry into a disk. Gas with too much angular momentum cannot fall straight inward, so it piles into orbit. Instead of a spherical plunge, the flow flattens, because rotation provides centrifugal support in the equatorial plane. The disk is not merely a byproduct, it is the mechanism that makes further collapse possible. Friction, turbulence, and magnetic stresses move angular momentum outward, letting some material spiral inward while other material is pushed to larger radii. The center accretes mass, while the disk becomes the system's angular momentum reservoir. Even the disk's thickness encodes physics. Hotter disks puff up, cooler disks settle into thinner layers. If you could see the gas in motion, you would watch spirals, shocks, and ripples, patterns that are really torque made visible. The disk is also a stage for chemistry and radiation. Dust grains collide and grow, molecules freeze onto surfaces, and ultraviolet light from nearby stars sculpts the outer layers. In the warm inner disk, silicates can anneal and crystallize, while farther out, water and carbon monoxide ices build mantles on grains. In young systems, jets and winds carve cavities through the surrounding cloud, creating bright bipolar lobes. Those outflows are not decorative. They are angular momentum relief valves that keep accretion going. Visually, it is a cosmic workshop, matter assembling under gravity, while rotation dictates the layout. The scene is busy, but the bookkeeping is strict. Mass moves inward only when angular momentum moves outward. So the opening claim is simple. Gravity does not create angular momentum, but it amplifies whatever is already there. A star's life is a long negotiation between gravity and pressure. For most of its life, thermal pressure from fusion supports the core against collapse. Hydrogen fuses into helium, and later stages fuse heavier elements, each step balancing gravity with heat. The chain of fuels is also a chain of timescales, because each successive stage yields less energy per unit mass. Rotation matters, but it is usually modest compared with gravity's binding energy, so the star remains close to spherical. Yet even modest rotation can influence mixing, magnetic activity, and the distribution of chemical elements. It can stir fresh hydrogen into the core, extend lifetimes slightly, and alter the surface abundances that astronomers read in spectra. The drama arrives when fusion ends and support fails, because then gravity regains control over the timetable. When massive stars exhaust fuel, the core contracts rapidly. The final fusion stages are brief, and the core can change dramatically in days or even hours. Silicon burning, for example, can be a frantic finale, building an iron core that cannot yield energy by further fusion. Angular momentum in the core spins up as radius shrinks, but the envelope can expand. The star can become a red supergiant with a slow surface and a fast interior, like a quiet exterior hiding a spinning engine. Internal transport determines how much spin reaches the final remnant, and that transport is neither simple nor fully settled. The star is layered like an onion, and each layer can rotate at its own pace. That layered rotation matters because the remnant is built from the deepest layers, not from the star's calm outer skin. Transport is the hidden plotline. Convection can mix angular momentum through bulk motion, moving it like a fluid conveyor belt. Magnetic fields can couple layers and enforce more uniform rotation, because field lines act like tensioned cords linking different radii. Differential rotation can also wind magnetic fields up, storing energy and changing the coupling strength over time. Stellar winds can remove angular momentum from the surface, especially in hot stars where radiation pressure drives mass loss. As the wind escapes, it carries away spin, and the star's surface slows like a skater extending their arms. Binaries can add or strip spin through tides and mass transfer, and those interactions can dominate the final outcome. In close pairs, tidal forces can synchronize rotation with the orbit, rewriting the star's spin history. A star that would have died slowly can be spun up, stripped, or merged into a very different ending. Historically, this was not obvious. Early stellar models often treated stars as non-rotating spheres, because that approximation worked surprisingly well for luminosities and lifetimes. As observations improved, rotation revealed itself through broadened spectral lines and star spot cycles. By the 20th century, astronomers could infer projected rotation speeds from how absorption lines smear out. Later, helioseismology and asteroseismology opened a new window, using oscillations to infer internal rotation profiles. The Sun, once assumed to be a simple rotator, turned out to have a complex interior with shear layers. The lesson was sobering. Stars can hide differential rotation and internal shear that surface measurements miss. If the surface is the face, seismology is the heartbeat. It also reminds us that rotation is not merely a number, but a profile that can change with depth. The end states are compact objects, and compact objects are spin machines. White dwarfs are Earth-sized remnants supported by electron degeneracy pressure, a quantum effect that resists compression when electrons are packed tightly. They can rotate from minutes to days, and rapid rotation changes their shape and stability. A fast white dwarf becomes slightly flattened, and its equator can bulge under centrifugal support. Their spin records the angular momentum left after mass loss, magnetic braking, and binary interactions. In some cases, rapid rotation can delay instabilities, buying time before more dramatic outcomes. Even a subtle change in spin can shift how close the star is to a critical threshold. White dwarfs also carry magnetic fields that can be strong by terrestrial standards. Some reach millions of Gauss, enough to reshape accretion flows and lock plasma to field lines. In some systems, magnetism channels accretion onto the poles, producing bright hotspots that pulse with rotation. In close binaries, a white dwarf can gain mass and angular momentum from a companion, and that transfer can transform a quiet remnant into a variable, energetic source. The accretion stream can arc like a glowing ribbon, then crash onto the surface in a shock that radiates in X-rays. Even in these comparatively gentle objects, rotation is a ledger of past events, and the ledger can be read as periodic flickers. The pulse is not just light, it is history repeating on a clock. Neutron stars push the story into extremes. They are about a solar mass packed into a sphere roughly tens of kilometers across, small enough to fit inside a metropolitan area. Their average density rivals atomic nuclei, and a teaspoon of their material would outweigh mountains. They are supported by neutron degeneracy and strong force pressure, not by heat. Their moments of inertia are tiny compared with their progenitor cores, so spin rates can soar. The crust is only a thin shell by radius, yet it sits above matter in phases we can only model. Between crust and core, theory predicts transitions, superfluid neutrons, superconducting protons, and mixtures whose properties set how the star responds to stress. A newborn neutron star can rotate many times per second. Some are born slower, depending on core coupling, magnetic torques, and explosion dynamics. The supernova itself is not perfectly symmetric, and asymmetries can redistribute angular momentum during the blast. Neutrinos carry away enormous energy, and their emission can also interact with the dynamics of the explosion. Accretion in binaries can spin them up again, recycling old neutron stars into millisecond pulsars. Conservation allows both birth spin and later spin-up to coexist, because the system's angular momentum can be stored, transferred, and reshuffled. What matters is not a single number, but the pathways that move that number around. When we time a pulsar, we are timing those pathways' final outcome. To visualize it, imagine a collapsing core as a dim, shrinking ember. The outer layers are thrown outward in a supernova, while the inner core compresses until neutrons dominate. The shockwave stalls, revives, and tears through the star, leaving an expanding shell that glows with radioactive afterlight. As the radius plunges, rotation accelerates, and the newborn neutron star becomes a spinning beacon. In some cases, the spin is so rapid that centrifugal forces nearly compete with gravity at the equator. That near breakup limit becomes a diagnostic of the star's internal stiffness, because only certain equations of state can withstand such strain. The faster the spin, the more the star's shape and gravity field deviate from a simple sphere. Pulsars are rotating neutron stars whose beams sweep past Earth. The beam comes from magnetized plasma guided by intense magnetic fields, and those fields can be trillions of times stronger than Earth's. Charged particles are forced to follow field lines, and they radiate as they accelerate through curved paths. As the star rotates, the beam acts like a lighthouse, cutting through space with metronomic regularity. The pulse period is the rotation period, measured with extraordinary precision. In radio telescopes, the pulses arrive as sharp spikes, and in X-rays they can appear as rhythmic flashes from hot polar caps. The very existence of a stable pulse tells you the star's magnetic geometry has remained coherent despite unimaginable stresses. That precision is evidence of stable rotation, not a coincidence. A pulsar's moment of inertia is huge for its size, and external torques are small compared with the star's stored rotational energy. Many pulsars keep time better than mechanical clocks over long baselines, and some rival the stability of atomic standards over certain intervals. Their slow spin down is measurable, and it tracks energy loss through radiation and particle winds. In timing data, the period lengthens by tiny fractions, yet those fractions accumulate into a clear trend. The timing residuals, plotted over years, look like a careful accountant's record of every missing fraction of a turn. This is why pulsars became tools, not just curiosities. Tools for navigation concepts, for plasma physics, and for tests of gravity. Now the tension enters. If angular momentum is conserved, why do pulsars change their spin at all? They change because they are not isolated. Magnetic dipole radiation and magnetospheric currents apply a braking torque, and the rotating field acts like a generator feeding energy into space. The star loses rotational kinetic energy and its period lengthens. The lost energy powers emission across radio, X-ray and gamma-ray bands, depending on magnetic field strength and particle acceleration. In simple models, the braking torque depends on magnetic field and spin rate, but real magnetospheres are complex and time variable. Plasma supply can wax and wane, and the torque can respond like a machine whose load is constantly changing. Even the angle between magnetic and spin axes can evolve, subtly changing how efficiently the star brakes. Sometimes the change is not smooth. Pulsars glitch, jumping suddenly to a slightly faster rotation, and the jump can occur in seconds. The leading explanation involves a superfluid interior that stores angular momentum in quantized vortices. Superfluids cannot rotate like ordinary fluids, so they form vortices whose circulation comes in discrete quantum units. Those vortices can pin to the crust, then unpin abruptly, and transfer angular momentum outward. The crust responds by spinning up, and the timing record shows a sharp step. It is as if a hidden flywheel briefly grabs the outer shell and forces it to catch up. The size of the jump and how often it repeats becomes a fingerprint of the star's internal coupling. Glitches turn rotation into a probe of exotic matter. The crust is a solid lattice under extreme pressure, and it can crack in starquakes as stresses build. The superfluid's coupling to the crust depends on microphysics we cannot reproduce on Earth, including interactions between vortices and nuclear structures. Some models include nuclear pasta, tangled shapes of matter that may affect how vortices pin and slide. Timing data becomes a seismology of neutron star interiors, where each glitch is a clue about hidden layers. The recovery after a glitch, sometimes quick, sometimes slow, suggests multiple components exchanging angular momentum imperfectly. A single event can reveal that the star is not one rigid body, but a set of coupled reservoirs. The question is almost philosophical. How does a star behave when its interior is both liquid and quantum-ordered, yet its crust is a brittle solid? The glitch story also links back to quantum spin indirectly. Superfluidity is a quantum state of matter, and its vortices are quantized angular momentum in bulk form. In neutron stars, quantum rules scale up to kilometers, which is both unsettling and elegant. The same conservation law governs both the vortices and the star's macroscopic rotation. It is a reminder that the microscopic and the cosmic are not separate worlds, only different scales of the same physics. When the crust jumps, it is quantum mechanics leaving a signature in a radio pulse train. We do not see the vortices directly, yet their bookkeeping appears in the arrival times of photons at a telescope. Magnetic fields complicate the picture further. Neutron stars can have fields trillions of times stronger than Earth's, and those fields evolve as the star ages. They channel plasma and shape the magnetosphere, which sets the torque and the emission geometry. The magnetic axis can be tilted relative to the spin axis, and that misalignment is what makes the lighthouse sweep possible. Magnetars add another extreme, where magnetic energy dominates and crustal stresses trigger bursts. In magnetars, twisting field lines can store energy, then release it in flares that briefly outshine entire galaxies in gamma rays. Even then, rotation remains part of the accounting, because magnetic activity can alter braking and timing noise. The pulse can jitter, the spin down can wander, and the ledger becomes noisier, but it never stops being a ledger. White dwarfs and neutron stars are not the end of collapse. If the core mass is high enough, no known pressure can halt gravity. The result is a black hole, and black holes can also spin. Unlike a solid star, a black hole has no surface, yet it can carry angular momentum as a property of spacetime itself. That idea once sounded paradoxical, but general relativity makes it precise. The spin is not a spinning material, but a twist in the geometry that surrounds the horizon. The object that rotates is the structure of spacetime, and everything nearby must respond. A rotating black hole is described by the Kerr solution, found in the early 1960s as relativity matured into a predictive astrophysical tool. Its spin is summarized by a dimensionless parameter that compares angular momentum to mass, often written as a value between 0 and nearly 1. Spin changes the event horizon structure and creates an ergosphere where spacetime is dragged around. Rotation becomes geometry, not just motion, and the distinction matters near the horizon. In the ergosphere, nothing can remain stationary relative to distant stars, because spacetime itself is moving. Even the language shifts here. Dragging is not friction, but the way mass energy reshapes the rules of motion. Frame dragging is not a metaphor in Kerr spacetime. Nearby orbits precess because spacetime itself is twisted, forcing even light and vacuum fluctuations to share the rotation. The innermost stable circular orbit moves inward for prograde motion and outward for retrograde motion relative to the whole spin. That shift changes how efficiently accretion converts gravity into radiation, because gas can orbit closer before plunging. In visual terms, the bright inner disk can tighten toward the horizon, and the last stable ring becomes a moving boundary set by spin. The difference is not subtle, because the deepest orbits are where the energy release is greatest. A fast-spinning hole can turn gravity into light with startling efficiency, and that efficiency is itself a clue to the hidden spin. So the opening claim is simple. In compact objects, rotation is not a detail, it is a controlling variable. Black hole spin is not always inherited cleanly. A collapsing core can deliver angular momentum, but explosions and fallback can modify it. Some material is ejected, then later rains back down, carrying its own angular momentum budget. Later accretion can spin the hole up or down, depending on disk orientation and whether the flow is aligned. Over long times, misaligned accretion can torque the system toward alignment, but the path can be messy. Mergers can produce a remnant with a new spin set by orbital angular momentum, and that orbital contribution can dwarf the original spins. The final black hole can emerge with a spin that reflects not one star's history, but a whole chain of interactions. When we infer spin, we're often inferring ancestry. Accretion disks are the universe's angular momentum processors. Infalling gas rarely falls straight in, so it forms a disk, and the disk's structure reflects the balance of gravity, pressure, and rotation. The disk heats through friction and turbulence, radiating strongly in X-rays near compact objects. Close to the center, temperatures can reach millions of kelvins, and the glow shifts to high-energy bands. In spectra, ion lines can appear broadened and skewed, shaped by Doppler shifts and gravitational redshift. To accrete, the gas must move angular momentum outward, because only then can it spiral inward without violating conservation. The disk is a conveyor belt where mass and angular momentum travel in opposite directions. When the inner disk brightens, you are watching angular momentum being exported in real time. That outward transport is the key physics. Microscopic viscosity is too small to explain observed accretion rates, so disks rely on turbulence and magnetic stresses. The magnetorotational instability can turn weak fields into strong angular momentum transport, even when the initial magnetism is faint. MRI links differential rotation to growing magnetic turbulence, enabling accretion on observed timescales. In simulations, tangled magnetic fields act like a break between neighboring rings of gas, pushing angular momentum outward while mass drifts inward. The process is subtle in equations but vivid in imagery: eddies, loops, and braided field lines churning like a storm. It is one of the great conceptual reversals in astrophysics. Magnetism, even when weak, can dominate the long-term evolution of a disk. Disks also launch jets, and jets are angular momentum exhaust pipes. Magnetic fields anchored in the disk can fling plasma outward along field lines, converting rotational energy into directed motion. Rotational energy can be extracted from the disk and, in some models, from the black hole itself through electromagnetic processes in the ergosphere. The jet carries energy, mass, and angular momentum away, clearing a path that lets the inner disk continue feeding the compact object. In some systems, the jet's direction stays stable for long periods, implying a persistent spin axis. The jet is not simply matter escaping, it is the system solving a conservation problem. Jets are relativistic in the most extreme systems. They appear in microquasars, active galactic nuclei, and gamma-ray bursts, each powered by accretion onto a compact engine. Their collimation suggests ordered magnetic structure near the engine, like invisible rails guiding the flow. Their power shows how efficiently gravity and rotation can be converted into directed outflow. In images, jets look like needles of light piercing interstellar gas, ending in shock-brightened knots where they slam into their surroundings. Along the jet, bright blobs can appear to move faster than light, an illusion created by near-light speed motion aimed close to our line of sight. Behind that illusion is a real fact. The flow is so fast that time and geometry become part of the visual story. Angular momentum loss is not optional, it is required. Without a way to shed angular momentum, matter stalls in orbit and accretion chokes, no matter how strong gravity is. Disks, winds, and jets provide the torque channels that let collapse proceed. The same conservation law that spins objects up also forces them to build escape routes. In that sense, rotation is both an amplifier and a constraint, an engine that demands an exhaust. The universe does not break the rule. It engineers pathways around the bottleneck. When we see a jet, we are seeing the cost of continued growth. Neutron stars in binaries show the same logic. Accretion transfers angular momentum to the star, spinning it up, and the spin can approach hundreds of rotations per second. The inflowing gas releases gravitational energy as X-rays when it strikes the surface or boundary layer. Magnetic fields can truncate the disk and regulate the torque, setting where the flow attaches to field lines. Some systems reach an equilibrium where spin-up and magnetic braking balance. When the balance shifts, the star can alternate between accretion-powered X-ray states and rotation-powered radio pulsar states. The same object can change its identity depending on which power source dominates. In a sense, the star carries two engines, and angular momentum decides which one is running. Pulsars also lose angular momentum through particle winds. The wind carries away rotational energy and angular momentum along open magnetic field lines, forming a magnetized outflow that can inflate nebulae. The Crab Nebula, for instance, is energized by a pulsar wind that drives shocks and lights up filaments. The braking index encodes how the torque depends on spin rate, and it can be measured when timing is stable enough. Deviations from simple models reveal evolving fields and magnetospheres, and they hint that the star's magnetic geometry is not fixed. Even small changes in plasma supply can alter the torque, leaving fingerprints in long-term timing. The wind is invisible by itself, yet its effects are written into the pulse period like a signature. Now the tension enters again, because collapse seems to create order from chaos. A collapsing cloud looks messy, yet the end product can be a clean disk and a fast rotator. The answer is that collapse is not creating order, it is concentrating a conserved quantity. The apparent organization is the geometry that conservation demands at small radii. Gravity compresses, rotation resists, and the compromise is a flattened spinning system. When you see a disk, you are seeing the shape of angular momentum made visible. The disk is not an accident. It is the only stable way to honor the ledger. These compact rotators become laboratories for fundamental physics. Neutron stars test dense matter equations of state through masses, radii, and spin limits, because the internal pressure law determines how much weight the star can hold. Rapid rotation sets a maximum before breakup, constraining internal stiffness. Measurements of the fastest spins tell us how close nature can approach that limit without tearing the star apart. Pulsar timing test gravity and plasma physics with clock-like stability, and binary pulsars add additional leverage through orbital dynamics. Each measurement is a way of asking what matter does when squeezed beyond nuclear density, and how space-time responds when mass moves that fast. The The remarkable point is that a distant radio signal can answer questions that particle accelerators cannot. Black holes test relativity in the strong field regime, spin effects horizon size, orbital precession, and light paths near the hole, bending trajectories into arcs and rings. Observations of disk spectra and ion line profiles infer inner disk radii and likely spins, because relativistic Doppler shifts and gravitational redshift sculpt the lines. Imaging and timing probe how spacetime behaves near the edge, where classical intuition fails. In that region, rotation is inseparable from geometry, and geometry dictates what can escape. Even the shadow of a black hole depends subtly on spin and viewing angle, because light is guided by curved spacetime. When the shadow's edge sharpens in an image, it is the boundary between what returns and what is lost. The newest laboratory is gravitational waves. When neutron stars or black holes merge, they radiate energy and angular momentum as ripples in spacetime, and those ripples travel outward essentially unimpeded. The waveform encodes masses, spins, and orientations, because those parameters change how the orbit tightens. LIGO, Virgo, and Cagra act as cosmic spin detectors by reading those phase evolutions. What looks like a faint chirp in a detector is, in reality, the final seconds of a relativistic dance. The signal rises in pitch because the orbit accelerates, and it ends abruptly when two horizons or two stars become one. Spin leaves fingerprints in spiral and merger. Aligned spins can speed or slow in spiral through spin-orbit coupling, shifting the rate at which the frequency rises. Misaligned spins cause precession that modulates the signal, like a wobble superimposed on the chirp. The final remnant spin is set by the balance between initial spins and orbital angular momentum radiated away. Even after merger, the ring-down frequencies depend on the remnant's mass and spin, offering a consistency check on relativity. In effect, the remnant rings like a struck bell, and its tone reveals its parameters. The waveform is a story of angular momentum being paid out, cycle by cycle, until the account is nearly empty. Neutron star mergers add another twist. Tidal deformation depends on the equation of state, and it affects the waveform by changing how easily each star is stretched. The post-merger remnant can be a hypermassive neutron star that spins rapidly before collapsing, supported temporarily by rotation and thermal pressure. The outcome determines whether a black hole forms promptly and how jets might launch. In some scenarios, the remnant's differential rotation can amplify magnetic fields, setting the stage for energetic outflows. The same conservation law that spun up the original stars now shapes the fate of the merged object. For a brief time, rotation can hold back gravity. Then, if it fails, collapse finishes the job. Gravitational waves also close the angular momentum ledger. They carry away a measurable fraction of the system's total, and detectors can infer that loss from the changing orbit. The universe can shed angular momentum without matter, using space-time itself as the transport medium. Conservation still holds, but the carrier changes. It is one of the most striking extensions of the same principle that spins up a collapsing cloud. When the waves pass Earth, they stretch and squeeze space by less than an atom's width, yet they encode the loss of enormous rotational energy. It invites a quiet question. What other invisible transports might nature use when matter cannot do the job? This chapter's arc is a single idea repeated at higher stakes. Stars inherit small spins from their birth environment, and those spins are shaped by turbulence, tides, and magnetic fields. Collapse shrinks radii and amplifies rotation by orders of magnitude, unless angular momentum is exported through disks and winds. Compact remnants reveal their interiors and their spacetime through how they spin and how they change. Every pulse, glitch, jet, and waveform is a different way of reading the same conserved quantity. The question is never whether the rule holds, but where the angular momentum goes. The central question remains in the background. Local systems can spin violently, yet the universe shows no preferred direction overall. Collapse amplifies what is available, but it does not set the cosmic total. The ledger can balance globally while producing extreme rotators locally. How can a cosmos with no universal spin still generate objects that whirl like drills? It is a quiet reminder that conservation laws govern both the grand average and the spectacular exception. Transition to the next scale. Individual stars can become near-perfect spin machines, but galaxies also rotate as coherent structures. Their rotation is shaped by the invisible scaffolding of dark matter and by the growth of the cosmic web. The next chapter follows angular momentum outward, from dead stars to living galaxies. Transition to the next scale. Individual stars can become near-perfect spin machines, but galaxies rotate as coherent systems across tens of thousands of light-years. On screen, a spiral galaxy hangs in blackness, its arms like pale brushstrokes, its core a bright knot of older stars, and its outskirts fading into a granular mist. The sense of stillness is an illusion created by distance and time, because every point of light is moving along an orbit that takes ages to complete. Even the dark lanes where dust hides starlight are part of the same rotating system, and they mark the places where cold gas collects and future stars are being prepared. A galaxy is not a rigid wheel, and it never rotates like a solid plate. It is a swarm of stars, gas and dust orbiting a shared gravitational center, and that center is defined by mass rather than by light. The disk is thin compared with its diameter, yet it contains orbits stacked like pages in a book, each page tilted only slightly from its neighbors. Above and below the disk, a faint stellar halo and globular clusters trace older, more eccentric paths, and their motions hint at ancient mergers that puffed the system up. If we could speed up time, the disk would look like a slow whirlpool made of points. Stars would stream past one another without collisions, because the typical distance between them is enormous compared with their sizes. Gas behaves differently, because clouds can collide, shock, and radiate energy away, and that difference helps explain why galaxies develop thin, cold disks at all. In a typical spiral galaxy, the Sun-like stars take hundreds of millions of years per orbit, and the numbers are so large they resist intuition. At the Sun's distance from the Milky Way center, one revolution takes about 230 million years, a span sometimes called a galactic year. If Earth's entire history were compressed into a single year, our planet would still not witness even one full galactic lap, and the dinosaurs would occupy only a few days. The disk looks steady only because our lives are short, and because the galaxy's dynamical timescales are vast. In long exposures, the arms appear as luminous ribbons, but the stars within those ribbons are not glued together by any rigid structure. The galaxy is more like a city of independent commuters than a spinning record, and the traffic patterns can persist even as individual travelers come and go. To measure rotation, astronomers do not watch stars crawl across the sky, because proper motions are tiny at these distances. Instead, they listen to light, breaking it into spectra and reading the subtle shifts as a kind of musical score. Rotation is measured through Doppler shifts, where spectral lines slide slightly in frequency, revealing speeds on opposite sides of the disk. The effect is tiny, yet it is systematic. One side is blue shifted as it approaches, and the other is red shifted as it recedes, producing a clean, mirrored signature of spin. The technique works especially well with gas, because gas produces narrow, identifiable lines. Cold hydrogen emits radio waves at 21 centimeters, a line produced by a subtle flip in the atom's electron-proton spin alignment, a transition so rare that it matters only because space contains so much hydrogen. That line can be mapped far beyond the bright stellar disk, and it becomes a tracer for the galaxy's outermost rotation, where the stars are too sparse to measure easily. Radio telescopes turn that whisper into a map. On screen, a false-color halo of hydrogen extends past the visible spiral arms, like a larger, transparent disk surrounding the bright one. The outer gas is often warped, tilted by interactions and by the halo's shape, yet it still obeys the same gravitational bookkeeping. Optical spectroscopy adds another view, and it often sharpens the inner details. Emission from ionized gas, such as hydrogen alpha, marks star-forming regions along spiral arms, and absorption lines from older stars provide a complementary measure of the stellar component. Each tracer has its biases, so the best rotation curves combine them carefully, correcting for inclination, internal turbulence, and the fact that gas can have non-circular motions. The opening claim is simple: galactic rotation is a map of gravity, because orbital speed depends on enclosed mass, and that dependence can be written as a relationship between velocity and radius. In plain terms, the faster something orbits at a given radius, the more mass must lie inside that orbit, whether we can see it or not. This is not a philosophical statement. It is a quantitative relationship that can be tested against data, and it either fits or it fails. If most mass sits near the bright center, outer orbits should slow with distance, because gravity weakens as you move away. Kepler's logic predicts a decline like planets around the Sun, where velocity falls as the inverse square root of radius. In that case, the outskirts would drift more slowly, and the rotation curve would slope downward, turning the galaxy into a scaled-up solar system. For decades, that expectation felt reasonable, and it matched the intuition that light traces mass. The luminous bulge and inner disk contain most of the visible stars, and starlight was once treated as a rough proxy for matter. Early astronomers could be forgiven for imagining that galaxies behaved like enlarged versions of our planetary neighborhood, only grander and more crowded. But spiral galaxies refuse that script, and they do so with stubborn clarity. Beyond the bright disk, orbital speeds stay roughly constant instead of falling, and the curve refuses to bend downward even where the stellar density collapses. The outer gas moves as if it is still deep in a gravitational well, even where starlight has thinned to almost nothing, and the discrepancy does not fade with better instruments. These plots are called rotation curves, and they are among the most persuasive diagnostic tools in extragalactic astronomy. They are the cleanest, most repeatable mismatch between light and gravity, and they show up with unsettling consistency across many systems. On a graph, the expected Keplerian drop looks like a fading tail, yet the observed line runs nearly flat, like a road that never descends. A flat curve carries a precise implication, and it is more mathematical than poetic. Flat curves mean mass keeps rising with radius, so the enclosed mass grows roughly in proportion to distance, even when the luminous matter does not. Something extends far beyond the visible stars and gas, and it does so in a way that is smooth rather than clumpy, because the rotation curves are smooth. Visually, imagine the galaxy's bright disk as a small island of light. Around it lies a much larger invisible continent of mass, shaping the motion of everything that tries to orbit. The stars we see are not the main structure. They are the illuminated surface, like city lights outlining only the inhabited coastline. You can try to hide the missing mass in faint stars or cold gas, and astronomers did consider those options seriously. The required amount is too large, and it would change other observations, including how galaxies form stars and how they absorb and emit radiation. A vast population of dim red dwarfs would leave signatures in stellar counts and chemical enrichment, because stars manufacture heavy elements and return them to gas over time. Cold gas is constrained as well, and the constraints come from multiple wavelengths that cross-check one another. Neutral hydrogen is detectable through radio emission, molecular gas through carbon monoxide lines, and ionized gas through optical emission and recombination lines. The inventories do not come close to what the rotation curves demand, and the mismatch persists even when the accounting is generous and the uncertainties are pushed to their limits. So the tension enters, and it is not a small one. The largest rotating systems we can map are dominated by something we cannot see, and the dominance grows stronger toward the outskirts where the disk becomes tenuous. The very regions where starlight fades are the regions where the gravitational requirement remains stubbornly high, as if the galaxy's true body extends far beyond its glow. Dark matter is the name for that unseen mass, and the name is deliberately descriptive rather than explanatory. It is defined by gravity first, and by composition only later, because the evidence arrives through motion and lensing rather than through direct detection. In this sense, dark matter is not a guess about particles. It is a label for a gravitational fact that demands a physical cause. In spirals, dark matter appears as a halo, and the word is chosen carefully. The halo is roughly spherical and far larger than the luminous disk, extending many times the galaxy's visible radius and enclosing it like a vast envelope. If the disk is a glowing coin, the halo is a dim sphere surrounding it, immense, weighty, and mostly silent. The halo's gravity holds the outer disk in fast orbit, and it changes what edge of the galaxy even means. Without it, the outer gas would not remain bound at observed speeds, and the galaxy would gradually shed its outskirts into intergalactic space. The flat rotation curve is, in effect, a stability statement about what must be there, even if it refuses to shine. Rotation curves are not a single anomaly, and their repetition is part of their power. They repeat across galaxy types, environments, and cosmic time, appearing in isolated spirals, in galaxies near companions, and in systems observed billions of years in the past. The details vary, yet the overall pattern is remarkably robust, as if nature is insisting on the same hidden ingredient over and over. The history matters here. because the evidence did not arrive as a single dramatic revelation. In the 1970s, Vera Rubin and Kent Ford used sensitive spectrographs to measure rotation in nearby spirals, and the flatness of the curves was difficult to dismiss. Their work did not invent the problem, but it made the evidence unavoidable and widely persuasive because it was careful, repeatable, and applied to multiple galaxies. Earlier hints had existed, and they now read like a prelude. Fritz Zwicky's cluster work pointed in the same direction, and so did studies of galaxy motions in groups. Yet the rotation curves brought the discrepancy into the everyday language of disk dynamics. Once you can draw the curve, the question becomes unavoidable. What is providing the extra pull? Low surface brightness galaxies sharpen the point because they remove the usual excuse that maybe we missed some stars. They have little starlight, yet their rotation demands strong gravity, as if the luminous component is only a minor garnish. These galaxies are diffuse and ghostly, with stars spread thinly across large areas, and their disks look like faint breath on a dark window. Because their disks contribute less mass, the dark component stands out more clearly, especially in the inner regions. In many cases, the inner rotation is already dominated by the halo, leaving little room to argue that ordinary matter is doing the job. The darkness is not just in the outskirts, it is everywhere, shaping the curve from the beginning. Dwarf galaxies do the same, and they do it in a regime where every photon is precious. Their stars move as if embedded in a massive extended potential well, and their internal velocities can be measured through stellar absorption lines and gas emission. Some dwarfs are so faint that only a few bright stars can be tracked, yet the gravitational demand remains, and it remains coherent. In these small systems, the ratio of dark to luminous mass can be extreme. A dwarf may contain a modest sprinkling of stars, while the halo that binds them outweighs the visible component by orders of magnitude. The galaxy becomes a lantern hung inside a much larger invisible structure, and the lantern's flicker tells us about the unseen frame. Now the story widens beyond single galaxies, because the same accounting problem appears at larger scales. Clusters of galaxies also move too fast for the visible mass, and the discrepancy becomes even more dramatic on these scales. A cluster is not a simple collection of galaxies, it is a gravitational ecosystem, with galaxies as bright inhabitants of a much larger potential. In the 1930s, Zwicky used galaxy velocities in the Coma cluster, applying the Viral theorem to connect motion with mass. The inferred mass exceeded the luminous matter by a large factor, and he called the missing component dunkle materie, dark matter. At the time, the claim was bold enough to be sidelined, yet it never truly went away, because the motions kept insisting. Modern data confirms the same pattern, and it adds new layers of measurement. Hot X-ray gas and galaxy motions require deep gravitational wells, and those wells are far deeper than starlight alone can justify. When we look in X-rays, clusters glow with plasma heated to tens of millions of degrees, and the glow outlines the shape of the potential that confines it. That plasma is not a minor detail, and it is often the dominant baryonic component in clusters. In many clusters, the hot intracluster medium contains more ordinary matter than all the galaxies combined, yet even that is not enough. The gas would escape unless an additional unseen mass holds it in place, and the temperatures themselves testify to the depth of the well. A cluster is a laboratory for gravity on huge scales, because it combines multiple traces in one object. It contains galaxies, diffuse plasma, and the dominant dark component, all interacting over billions of years. The galaxies orbit like bees around a hive, while the gas fills the space between them like a thin, scorching atmosphere, and the dark matter provides the hive's weight. Rotation is not the only probe, and the documentary's story becomes richer when we add light bending. Gravity also bends light, and lensing measures mass without caring what it is, because space-time curvature responds to energy and mass directly. This is one of the most elegant tests in astronomy, since it does not require assumptions about equilibrium or internal motions, only geometry and relativity. Strong lensing makes arcs and multiple images, and it can be visually startling. The geometry reveals the mass distribution in the lensing object, and the arcs can be so bright and sharp that they look like brushstrokes of blue paint across a dark canvas. A distant galaxy is stretched into a crescent, duplicated and rearranged by an intervening cluster, turning the sky into a natural hall of mirrors. Weak lensing is subtler but broader, and it is built from patience and statistics. Background galaxies are stretched statistically, mapping mass across wide areas, and the signal emerges only when many shapes are averaged. Individually, each galaxy is noisy, but together they reveal a coherent distortion field, like wind patterns inferred from the lean of tall grass. When those distortion maps are reconstructed, the result is striking, and it often feels like an X-ray of gravity itself. The mass distribution often peaks where there is little light, and it extends beyond the visible boundaries of the cluster. The lensing map becomes a shadow image of the hidden scaffold, and the scaffold looks smooth, extended, and dominant. Lensing agrees with rotation curves and cluster dynamics, and that agreement is the point. The unseen mass is not a quirk of one method, and it is not easily erased by changing a single assumption about gas physics or stellar populations. Different measurements, using different physics, converge on the same conclusion, and convergence is one of science's most reliable signals. So the opening claim is simple, and it becomes stronger with every independent test. Dark matter is inferred independently by motions and by light bending, and the inferences match, often to impressive precision. In science, that kind of convergence is rare, and it carries weight because it reduces the chance that we are chasing a single systematic error. This match raises a deeper question, and it brings angular momentum back into the frame. If dark matter dominates the mass, does it also dominate the angular momentum story, shaping how galaxies acquire and keep their spin? In other words, is the visible disk merely a tracer of a deeper rotational history written in darkness, with the halo as the true reservoir? Galaxies spin, but they did not start as disks, and they did not begin as neat spirals. They grew from tiny density fluctuations in an expanding universe, where matter was distributed almost uniformly with only faint ripples. Those ripples are preserved in the cosmic microwave background as a pattern of temperature variations, and the pattern is a kind of fossil of the initial conditions. In the early universe, matter was nearly uniform, and the deviations were small enough to describe statistically. Small overdensities grew by gravity pulling in surrounding material, and the growth was slow at first, then faster as structures became denser. The process is hierarchical, meaning small objects form earlier and merge into larger ones, building complexity through repeated assembly. Dark matter collapses first because it does not radiate, and that single fact changes everything. It forms halos that act as gravitational scaffolds, and because it cannot cool by emitting light, it remains puffy and extended. That very inability to shed energy becomes a defining feature of the cosmic architecture, because it lets dark matter hold a large, stable volume. Baryonic gas falls into those halos later, and it arrives with heat and turbulence. It shocks, heats, cools, and gradually settles toward the center, and each stage leaves an imprint on the final galaxy. As gas plunges in, it can be heated to the halo's virial temperature, then cool through atomic and molecular emission, turning thermal energy into photons that escape into space. Cooling is not instantaneous, and it is not guaranteed. It depends on density, metallicity, and the presence of radiation fields, and it can be slowed by feedback from star formation that reheats the gas. Yet over time, enough gas can lose energy to form a rotating disk in the halo's central region, and the disk's thinness is a sign that much of that energy has been radiated away. Halos are not born spinning fast, and they do not need a primordial cosmic whirl to rotate. Their angular momentum is acquired through tidal torques during structure formation, when neighbouring density peaks pull on each other unevenly. The key is asymmetry. Perfectly spherical collapse would not generate a net twist, because every pull would cancel its opposite. Tidal torque theory is the accessible picture, and it connects local gravity to global structure. Neighbouring lumps of matter pull unevenly, applying a net twist over time, and the twist accumulates while the proto-halo is still expanding with the universe. The torque is strongest before collapse becomes fully nonlinear, when the material still has a large lever arm and can be nudged efficiently. The torque is weak, but it acts for long durations, and long durations matter in cosmology. As collapse proceeds, the same angular momentum becomes dynamically important, because the material moves inward and speeds up. A slow cosmic twist becomes a fast local rotation, simply by changing scale, and the change is enforced by conservation. This is conservation at work again, but now in a setting that spans millions of light years. Gravity amplifies a small initial twist by shrinking the effective lever arm, and the result is a rotating halo with a measurable spin parameter. The physics is familiar from ice skaters, yet the stage is cosmic, and the consequences shape entire galaxies. In simulations, halos end with a characteristic spin distribution, and the result is surprisingly consistent. Most halos have modest dimensionless spin, and a few are higher, producing a broad range of disk sizes and rotation properties. The distribution is not arbitrary. It emerges repeatedly in different numerical experiments, suggesting it is a natural outcome of gravitational growth in a web-like universe. The spin axis is not fixed by a universal direction, and it is not stamped onto the cosmos like a compass needle. It emerges from local interactions in the cosmic web, where filaments and sheets channel matter into halos. A galaxy's orientation is, in part, a fossil record of its neighbourhood's geometry, and that geometry can evolve as the galaxy accretes new material. Mergers add another pathway, and they can both build and destroy order. When halos collide, orbital angular momentum can become internal rotation, and the outcome depends on mass ratio, impact parameter, and gas content. A gentle merger can spin up a disk, while a violent one can scramble it into an elliptical remnant, converting ordered rotation into random motions. Some of that angular momentum ends up in the dark matter, and some is transferred to gas, stars, and extended tidal debris. That debris can form long streams and shells, and it can remain visible for billions of years as a faint record of past encounters. In deep images, those faint streams are visible as ghostly arcs, evidence that angular momentum has been redistributed rather than destroyed. Now the tension enters again, and it is a tension between dominance and visibility. The dominant mass is dark, yet the luminous disk records a coherent spin, often in a thin, orderly plane. The disk is fragile in some respects, so its persistence suggests that the system's angular momentum has been managed carefully over time, avoiding too many catastrophic disruptions. Baryons do not simply trace the halo, even though they fall into it. Gas can cool and lose energy, but it cannot lose angular momentum as easily unless torques or frictional processes act. If gas were to shed too much angular momentum, it would collapse too far inward, producing disks that are too small compared with what we observe, and that mismatch has been a long-standing challenge for galaxy formation models. As gas settles, it forms a rotating disk, and that disk becomes a compromise written in motion. The disk is the baryonic balance between gravity inward and rotation outward, and it becomes the stage for star formation and chemical evolution. Within the disk, viscosity, turbulence, and gravitational instabilities can move angular momentum around, allowing some gas to drift inward while other material migrates outward. The disk is also layered, and the layers are visible when galaxies are seen edge-on. Cold molecular clouds occupy thin lanes, warm atomic gas spreads more broadly, and hot ionized gas rises into a thicker atmosphere. Each component responds differently to gravity and feedback, yet all participate in the galaxy's overall rotation, and together they form a dynamic multi-phase ecosystem. Spiral arms do not prove rigid rotation, and that distinction matters for understanding what we see. They are patterns that move through the disk, like density waves, and they can persist even though the material in the disk is constantly changing. The arms are not fixed spokes. They are organized traffic jams where orbits crowd together and gas is compressed. Stars and gas orbit at different speeds at different radii, and that differential rotation would wind up any material arm quickly. The spiral structure persists because the pattern is not a fixed set of stars, and because self-gravity and resonances help maintain the wave. Near certain radii, material can exchange angular momentum efficiently with the pattern, and those exchanges can sculpt the disk over long times. Density waves compress gas as it passes through, and compression changes chemistry and temperature. Compression triggers star formation, making arms bright without being material spokes, and the newborn stars light the arms with blue clusters and glowing nebulae. A spiral arm is partly a map of recent star formation, not a permanent structure, and its brightness is a kind of timestamp. Bars add another torque channel, and they can be powerful engines of redistribution. A bar can transfer angular momentum outward and drive gas inward, reshaping the galaxy over time and building central concentrations. In images, bars look like luminous bridges across the center, and they can funnel gas toward the inner kiloparsec, where gravity becomes steep and dynamics accelerate. Gas inflow can feed central starbursts and black hole growth, tying rotation to long-term evolution. The galaxy's rotation becomes a pipeline for change, transporting fuel from the outskirts to the core. The same angular momentum that supports the disk must be redistributed for gas to reach the center, and that redistribution leaves signatures in rings, resonances, and bursts of star formation. Feedback complicates the pipeline, because stars do not form quietly. Supernovae and stellar winds inject energy and momentum into the interstellar medium, stirring turbulence and heating gas. The result is a disk that is not perfectly calm, but alive with expanding bubbles and shock fronts, and those disturbances can thicken the disk over time. Outflows can remove low angular momentum gas, and that selective removal can matter. That process can reshape the inner rotation curve and alter disk thickness, because what remains has a different angular momentum distribution. In some galaxies, fountains of gas rise above the disk and rain back down, mixing material across radii and blurring the boundary between disk and halo. Active galactic nuclei can do the same at higher power, and their reach can be startling. Black hole feedback can heat gas and suppress further cooling, and in extreme cases it can drive jets that carve cavities in surrounding plasma. The central engine is small, yet its influence can reach far into the halo, and it can change how efficiently baryons settle into the rotating disk. So the opening claim is simple, but it carries layers of cause and effect. The observed rotation is not just gravity, but gravity filtered through cooling and feedback, and that filtering determines which baryons become stars. The rotation curve is therefore both a dynamical measurement and a record of a galaxy's history, written in speed rather than in words. This filtering can solve some puzzles and create others, because it couples visible and invisible matter. It can flatten central density profiles and regulate star formation efficiency, yet it can also make interpretation harder by coupling baryons and dark matter. When gas flows inward or outward, the gravitational potential changes, and the halo can respond, subtly reshaping the distribution we are trying to infer. Yet the core evidence remains, and it remains most cleanly in the outskirts. Even after baryonic physics, many galaxies still require massive dark halos, especially in their outer regions where baryons are scarce and the gas is thin. The simplest way to say it is that ordinary matter cannot account for the observed speeds, and the numbers do not bend to preference. Rotation curves become a joint constraint, and that is why they are so valued. They test both the dark matter distribution and the baryonic response, and they force models to match not only total mass but its radial arrangement. A good model must reproduce the shape of the curve, not merely its overall scale, because the curve encodes where the mass sits. This is why galaxies are central to the documentary's question, and why their spin feels like a clue. They are huge angular momentum reservoirs that still obey strict accounting, and they reveal hidden mass through the disciplined motion of orbiting gas. A rotation curve is a ledger entry written in kilometers per second, and the ledger does not accept missing pages. Now scale up again, because galaxies do not live alone. Galaxies live in groups, clusters, and filaments that form the cosmic web, and the web is visible in surveys as a lacework of structure. In wide-field maps, galaxies outline strands and knots, with vast voids between them, and the pattern looks like a three-dimensional network cast onto the sky. The cosmic web is built by gravity acting on initial fluctuations, and dark matter sets the framework. Dark matter defines the filaments, and baryons light them up because gas falls into the same potential wells and forms stars. The luminous universe is, in a sense, a dye injected into a dark flow, revealing currents that would otherwise be invisible. In this web, flows are not random, and they are not gentle. Matter streams along filaments into nodes, feeding halos and driving mergers, and those streams carry angular momentum. The direction from which matter arrives can influence the eventual spin of the galaxy that forms, because accretion is often anisotropic, arriving in preferred planes and along preferred paths. These flows can imprint alignments, and the possibility is scientifically provocative. Spins can correlate with filament directions depending on mass and formation history, and the correlations are subtle rather than absolute. A galaxy may tend to align one way in a filament, while a more massive system may show a different tendency, as mergers and accretion histories change. Measuring large-scale angular momentum is difficult, and the difficulty is not just technical, but geometric. We observe projected shapes, limited traces, and noisy velocity fields, and we must disentangle rotation from random motions. Inclination matters, dust obscures, and distant galaxies offer only coarse data, so the signal must be extracted carefully from imperfect views. Integral field spectroscopy helps by mapping velocities across a galaxy's face. turning a smear of light into a two-dimensional velocity field. On screen, a colour map spreads across a disk, blue on one side, red on the other, revealing rotation as a gradient rather than a single number. Even so, the outermost regions remain challenging, because the signal is faint and the gas can be disturbed by interactions, warps and inflows. Yet hints persist in surveys and simulations, and they keep the question alive. Galaxy spins may align weakly with their environment, especially in filaments, and the effect can depend on how recently a galaxy accreted material. If these alignments are real, they would be another way the web writes its geometry into galaxies, leaving a statistical fingerprint in the sky. Clusters show coherent motions too, and their growth is directional. Subclusters fall in along preferred directions, carrying orbital angular momentum, and the infall is guided by filaments that act like cosmic highways. In simulations, clusters grow by anisotropic accretion, not by perfectly symmetric collapse, and the asymmetry can persist as long-lived internal motions. Some of that orbital angular momentum becomes internal rotation of the cluster, and some remains as streaming motions. Some remains as long-lived streaming motions, because relaxation on these scales takes enormous time, often longer than the age of the universe in detail. A cluster can remember the direction of its growth for billions of years, and that memory can be read in velocity substructure and gas patterns. Even the intra-cluster gas can swirl, and X-ray images sometimes reveal it like weather. X-ray observations reveal sloshing and cold fronts that trace bulk angular momentum, producing sharp edges in temperature and density. These features look like ripples in a hot, thin ocean trapped by gravity, and they show that even diffuse plasma can carry the imprint of past encounters. But the largest question is not whether structures spin locally, because local spin is everywhere we look. It is whether the universe spins globally, as if there were an overall cosmic rotation. This is where awe meets restraint, because the cosmos appears remarkably impartial, and the data demands caution. The cosmic ledger idea returns here, and it becomes a statement about symmetry. Local spins can be huge, yet the large-scale universe looks statistically isotropic, meaning it has no preferred direction when averaged over vast distances. The sky, in aggregate, does not lean, and that neutrality is one of the deepest observational facts in cosmology. The cosmic microwave background is nearly uniform, and its tiny anisotropies are measured with exquisite precision. Its anisotropies constrain any overall rotation to be extremely small, because a rotating universe would imprint characteristic patterns in that ancient light. The microwave background is a snapshot from when the universe was about 380,000 years old, and it carries the memory of conditions long before galaxies existed. That constraint does not forbid spinning galaxies, and it does not weaken the rotation curves. It implies their angular momenta cancel on the larger scales, so that no global axis emerges, even when individual systems spin rapidly. The universe can host countless rotating systems, while remaining directionless overall, and that coexistence is a clue to how structure forms. Cancellation can happen naturally, and it does not require fine-tuning. If spin directions are broadly random, the vector sum trends towards zero in large volumes, even when individual magnitudes are large. This is a statistical outcome, not a special tuning, and it is exactly what we expect when many local torques act independently. Structure formation can still generate local torques, and those torques are enough. Those torques create spins without creating a preferred cosmic axis, because the torques arise from local asymmetries rather than from a universal rotation. The cosmic web can twist without the cosmos itself turning, and the distinction matters for interpreting what the background radiation tells us. So the tension becomes a kind of balance, and it is one of the chapter's central observations. The universe builds rotating islands inside an ocean with no global swirl, and the islands inherit their spin from nearby gravitational conversations. Each galaxy is a local solution to a global neutrality, and the solution is written in the shape of its rotation curve. Dark matter makes the balance possible, and it does so in more than one way. It provides deep potentials that preserve rotation while the universe expands, and it stabilizes disks against disruption in their outer regions. The halo is both a gravitational anchor and a memory of early structure formation, holding on to angular momentum that baryons can later sample. It also hides most of the mass from our eyes, and that invisibility changes how we do astronomy. We infer the scaffold by how luminous matter moves within it, and by how background light is bent around it. In a profound sense, We map the invisible by watching how it choreographs the visible, turning motion and distortion into a kind of cosmic imaging. Rotation curves are the simplest reading of that scaffold because they translate directly into mass profiles. Lensing is the most direct because it measures gravity without dynamics, and the two methods reinforce each other. When both agree, the conclusion becomes difficult to evade, and the halo stops being a hypothesis and becomes a required component of the story. Together they tell one story, and it is both humbling and clarifying. The visible galaxy is a tracer, and the dominant structure is an unseen halo, extending far beyond the last bright stars. The galaxy we photograph is only the inner luminous layer of a much larger object, and the larger object is what governs the orbits. Now the stakes rise because the question of spin points backward in time. If galaxies inherit spin from early cosmic conditions, the origin of angular momentum must be set even earlier, before disks and even before halos fully formed. That pushes the question back toward the initial conditions of the universe, where tiny asymmetries were first amplified into structure. We have followed conservation from particles to stars to galaxies, and the rule never breaks. The rule never breaks, but it does not explain the initial twist, the seed asymmetry that talks could amplify into rotation. Conservation keeps the books, yet it does not write the first entry, and that first entry is where cosmology begins to feel like archaeology. The next step is to go back toward the early universe, where the ledger's first lines were written. Tiny fluctuations grew into halos, and halos set the stage for every spin, from the smallest dwarf to the largest cluster. The rotation curves we measure today are echoes of that ancient growth, and the echoes carry information about what the universe was made of and how it evolved. Transition. To understand why galaxies rotate the way they do, we return to the beginning, where the first asymmetries were written. Stand still for a moment, then notice how quickly "still" becomes a slippery word in cosmology, where even the stage is moving. Remember that the motion never began with planets or galaxies, or even with stars forming in dark halos. It began with the universe hot, dense, and expanding, where defining rotation requires care, and where before and after are stitched to space-time itself. The Big Bang is not an explosion into empty space, with matter flying outward from a central point. It is the expansion of space itself, with distances growing between nearly all comoving points, even when those points are not moving through space locally. In that setting, moving outward is not the same as travelling away through pre-existing space, because the metric that measures distance is changing. The early universe is better described as a fluid of energy and particles, cooling as it expands, with pressure, density, and temperature evolving together. That distinction matters because rotation is usually defined relative to a frame, and frames are not automatic in a curved, expanding space-time. In everyday life, a rotating frame reveals itself through centrifugal effects and Coriolis deflections, which you can feel in a spinning ride or see in a deflected trajectory. In cosmology, the natural frame is tied to the average flow of matter and radiation, the frame in which the universe looks as uniform as possible. The cosmic microwave background defines that frame with unusual clarity, because it provides a near-universal rest standard written across the sky. If you move relative to that CMB frame, the sky shows a dipole pattern, a simple two-lobed signature painted on the oldest light. One direction looks slightly hotter, the opposite slightly cooler, because of Doppler shift as our motion blue shifts photons ahead and red shifts photons behind. That dipole is our motion, not the universe's global spin, and it is measured with exquisite precision by multiple missions. It is the first reminder that apparent rotation can be a coordinate choice, while real vorticity is a physical property of the cosmic fluid. In general relativity, expansion and rotation can coexist, but they leave different fingerprints, and those fingerprints are not subtle once you know where to look. Expansion is encoded in the changing scale factor, which stretches wavelengths and dilutes densities, turning hot radiation into cooler radiation as the universe grows. Rotation would appear as vorticity in the cosmic fluid and as frame dragging on the larger scales, a kind of gravitational twist that affects inertial frames. A globally rotating universe would pick out a preferred axis, and that axis would show up in the oldest light, especially in the largest angular patterns on the sky. So the opening claim is simple. The early universe sets the initial conditions, but it also sets the rules for what spin can mean. At the earliest times, the universe was dominated by radiation and high-energy particles, and the energy density was so high that familiar matter could not hold together. Temperatures were extreme, so matter existed as a plasma of electrons, nuclei, and photons scattering constantly, with mean free paths so short that light behaved like part of the fluid. Pressure was enormous, and gravity was competing with that pressure while expansion pulled everything apart, creating a dynamic balance that changed from moment to moment. In this era, small inhomogeneities mattered because they were the only seeds available, and because later structure could only grow from what already existed. As the universe expanded, it cooled, and the cooling was not just a drop in temperature on a thermometer. It was a systematic redshifting of radiation, a dilution of number densities, and a slowing of interaction rates as particles became less crowded. The early plasma supported waves, flows, and tiny velocity fields, but it was also remarkably uniform, with fluctuations at the level of parts in 100,000. That near uniformity is itself a clue, because a universe that begins chaotic would not naturally settle into such smoothness without a mechanism. Those seeds did not come from classical stirring, because there were no stars, no winds, and no rotating disks to mix the cosmic soup. They came from quantum fluctuations, the unavoidable jitter of fields even in their lowest energy states, the same principle that gives atoms their zero-point motion. Quantum uncertainty does not wait for stars or atoms to exist. It is present in the fields that fill space-time, and it produces tiny variations in energy density, pressure, and gravitational potential. On microscopic scales, those variations are fleeting and normally average away because positive and negative deviations cancel when you look over larger volumes. But the early universe had a mechanism that could freeze them into history, turning ephemeral ripples into the initial conditions for galaxies. That mechanism is inflation, a brief period of accelerated expansion that stretched tiny regions to cosmic size, carrying quantum-scale irregularities outward like ink pulled into long filaments. Inflation is invoked to explain several otherwise puzzling facts, and it entered cosmology historically as an attempt to make sense of what the Big Bang model seemed to require. It can smooth away initial curvature, making the universe appear spatially flat on large scales, which matches precision measurements of the CMB. It can also explain why distant regions share nearly the same temperature, because they were once in causal contact before being driven apart. Most importantly for this story, inflation can dilute many kinds of large-scale anisotropy, including shear and any coherent universe-wide rotation. To picture inflation, imagine a tiny patch of space that is already almost uniform, then watch it balloon so fast that any initial wrinkles become imperceptible. The expansion is not like matter rushing outward, but like the ruler itself stretching, so that co-moving points separate faster than light without violating relativity. What matters physically is that causal processes cannot keep up, so a small, causally connected region becomes the seed for an enormous observable domain. In that process, gradients are flattened, and directional features are pushed beyond the horizon, leaving behind a universe that looks statistically the same in every direction. Inflation acts like a cosmic reset of large-scale structure, but it is a reset with a very specific signature. Any pre-existing shear, curvature gradients, or global rotation would be exponentially suppressed as space expands by huge factors, sometimes quoted as dozens of e-folds. If the universe began with some net vorticity, inflation would drive it toward near zero in the observable region, because vorticity density dilutes rapidly as the scale factor grows. The result would be a cosmos that looks directionless, even if the pre-inflation state was more complicated than we can now observe. This is not a philosophical preference for symmetry, and it is not merely an aesthetic choice in the equations. It is a dynamical statement about how fast expansion erases certain patterns, especially those that require coherence over vast distances. Rotation, like any conserved quantity, can be spread thin by expansion when the relevant density scales away, leaving a remnant too small to detect. Inflation does not violate conservation, but it can make a global spin practically undetectable, like a drop of dye dispersed into an ocean until no instrument can find its original streak. Yet inflation does not erase everything, and that is where the story becomes productive rather than empty. It takes quantum fluctuations and stretches them into classical-looking perturbations, because the modes are pushed outside the horizon and effectively freeze in amplitude. The fluctuations become a spectrum of density variations, with a characteristic near-scale invariant form, meaning there is similar power across a wide range of scales. Those variations are small, but they are coherent across enormous distances, and coherence is exactly what gravity needs to build structure. When inflation ends, the universe reheats, filling space again with particles and radiation, but now with a faint imprint of those stretched fluctuations. The energy that drove inflation is converted into a hot bath, restoring the conditions for the standard hot Big Bang evolution. The universe resumes its more familiar expansion, with radiation dominating first, then matter taking over later. Through it all, the perturbations remain as slight over and under densities, like a barely visible texture on an otherwise smooth surface. The cosmic microwave background is where we see those perturbations most cleanly, because it is the earliest light we can observe directly. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, photons stopped scattering frequently, and the mean free path of light suddenly became enormous. Light decoupled and began free streaming, carrying a snapshot of density and velocity patterns at that time, preserved by the near vacuum of later expansion. The CMB's temperature anisotropies are tiny, about 1 part in 100,000, yet they are the blueprint of later structure. Visually, the CMB is a sphere around us, and every direction is a different line of sight back to the same epoch. The mottled pattern is not noise, but information, and its statistics can be decomposed into spherical harmonics like notes in a chord. Large angular scales correspond to the biggest primordial modes, while smaller scales capture the acoustic physics of the plasma. When the maps are coloured and projected, they look like abstract art. Yet every patch is a measurement of the early universe's physical state. The peaks and troughs in the CMB power spectrum encode acoustic oscillations, which are literally sound waves in the primordial plasma. Gravity tried to compress overdense regions, while radiation pressure pushed back, creating oscillations whose phases were set by the initial conditions. The pattern of peaks reveals the universe's composition and geometry, including the baryon density, dark matter density, and the angular diameter distance to last scattering. It also tells us the initial perturbations were simple and nearly Gaussian, consistent with inflationary origins because non-Gaussianity would distort the peak structure and higher-order correlations. These acoustic peaks are more than a technical triumph, because they show that the early universe behaved like a well-understood physical system. The plasma had a sound speed, a viscosity-like damping scale, and a horizon size that set the largest coherent oscillations. Photon diffusion, often called silk damping, smoothed fluctuations on small scales, leaving a characteristic fall-off in power. Each of these effects is a piece of the same story. The early universe was a fluid with measurable properties, and it left a record we can test. Now the question sharpens because the universe looks so uniform at the beginning, yet so rotational later. If inflation smooths the universe and suppresses global rotation, why does everything later spin, from galaxies to stars to planets? The answer begins with the difference between global rotation and local angular momentum, a distinction that is easy to miss when looking at spinning disks in the night sky. A universe can have no net spin and still generate spinning structures, just as a calm lake can have many small whirlpools without the entire lake rotating. Local angular momentum can arise through gravitational interactions among perturbations, even when the global sum cancels. Conservation governs each interaction, but it does not require every region to share the same sign, and it does not demand a single cosmic axis. To see how, we follow perturbations forward in time, from linear ripples to non-linear structures. After decoupling, matter begins to dominate the growth of structure, because radiation no longer provides the main pressure support on large scales. Overdensities attract surrounding matter, and the contrast between dense and less dense regions increases, a process described by gravitational instability. Dark matter collapses first because it does not couple to light, so it cannot be held up by radiation pressure, and it begins clumping even before recombination in a limited way. It forms halos and filaments that guide baryonic gas later, creating the scaffolding of the cosmic web. In simulations, that web is a striking visual, sheets and filaments intersecting at nodes with voids expanding between them. Matter flows along these filaments like traffic on intergalactic highways, feeding growing halos at the intersections. The geometry is not accidental, because gravity amplifies anisotropies, and collapse happens fastest along the shortest axis of an overdense region. The result is a universe that becomes structured in a highly directional way locally, even while remaining statistically isotropic globally. In the simplest picture, a perfectly spherical overdensity collapses without acquiring net spin, because symmetry forbids a preferred direction. Every inward pull is balanced by an opposite pull, so there is no torque, and the angular momentum remains zero. Real perturbations are not perfect spheres, and their environments are not symmetric because nearby overdensities and underdensities create uneven gravitational fields. Nearby structures pull unevenly, and that asymmetry generates tidal torques, the same basic mechanism that raises tides on Earth, but now applied to proto-galaxies. Tidal torque theory is the key bridge from density ripples to rotation, and it is one of the most important ideas linking early universe statistics to galaxy properties. A proto-halo has an irregular mass distribution, meaning its inertia tensor is not perfectly aligned with the surrounding gravitational potential. It sits in an external gravitational field created by neighbouring structures, and that field has gradients across the proto-halo's extent. The external field exerts different forces across the proto-halo, producing a torque, and that torque changes the proto-halo's angular momentum over time, even though the total angular momentum of the larger region remains conserved. In more concrete terms, torque requires a lever arm, and the early proto-halo is large, diffuse, and extended across a region where the tidal field varies. Small differences in acceleration across that region accumulate over cosmic time, slowly building a spin vector. The direction of that spin depends on the relative orientation between the proto-halo's shape and the tidal field, which is why spin is correlated with environment in subtle ways. This is not a single push, but a long gravitational conversation between a forming object and its neighbourhood. The effect is strongest before collapse becomes nonlinear, and that timing is essential to why galaxies end up with the spins they do. Early on, the proto-halo is large, so it has a large lever arm, and small forces can accumulate significant angular momentum over many expansion times. As collapse proceeds, the lever arm shrinks and the torque efficiency drops, because the object becomes more compact and less susceptible to differential pulls. By the time the halo virializes, reaching a quasi-equilibrium between kinetic and potential energy, much of its spin has already been set. This is a crucial point for the documentary's central question, because it separates the origin of spin from the later amplification of spin. Spin can be generated locally without any primordial cosmic whirl, and it can be generated early, before the object even resembles a galaxy. The universe does not need to start rotating like a giant top for galaxies to rotate. It only needs small asymmetries and gravitational coupling among growing structures, which are unavoidable given the initial perturbations. Angular momentum is still conserved in the full system, but the conservation is distributed, and that distribution can look counterintuitive. When one region gains angular momentum in one direction, another region gains it in the opposite direction, or the surrounding tidal field carries the counterbalance in its own motions. The ledger is kept, but the entries are distributed across space and across components, including dark matter, gas, and the larger scale flows of the cosmic web. In practice, you cannot close the accounting by looking at a single galaxy alone, because the environment holds part of the story. As halos form, baryonic gas falls in and shocks, heating to the virial temperature, and the heating can be dramatic in massive systems. Gas can radiate energy away and cool, which allows it to settle into a disk, but the cooling is mediated by atomic transitions, molecular lines, and later by metals produced by stars. Cooling removes energy but does not easily remove angular momentum, so the gas retains much of the halo's spin, at least in broad terms. The result is a rotating disk embedded in a larger, more slowly rotating halo, with angular momentum partitioned between components. This is where the familiar amplification returns, because contraction turns modest rotation into rapid rotation. As gas contracts from halo scales to disk scales, its rotation speed increases to conserve angular momentum, and the disk becomes thin as random motions are damped by dissipation. The same principle that spins up a collapsing star also spins up a forming galaxy, and it is the same principle that makes an ice skater rotate faster when pulling in their arms. Gravity concentrates, angular momentum resists, and the compromise is a flattened, rotating structure, often with spiral patterns shaped by density waves and instabilities. In vivid terms, the disk is a kind of cosmic record player, with stars tracing nearly circular orbits while gas clouds collide and form new generations of stars. The rotation curve, the way speed changes with radius, reveals the presence of dark matter, because visible matter alone cannot explain the observed velocities. So spin is not just a decorative feature of galaxies. It is a diagnostic, a measurable dynamical state that exposes the hidden mass distribution and the history of accretion and mergers. But the early universe story is not finished until we address the forbidden possibility, the idea that refuses to disappear because it is so simple. Could the universe itself rotate even slightly, and could that rotation have seeded everything else? General relativity allows rotating cosmological solutions, and historically these solutions were explored as soon as the field equations were understood well enough to permit exact models. Gödel's universe is the famous example, a rotating spacetime with closed time-like curves where the geometry is twisted enough to allow paths that return to their own past. It is mathematically consistent, and it taught physicists that the equations permit surprising global structures, but it does not resemble our universe, because it has no expansion like the observed Hubble flow, and it violates the observed large-scale isotropy that the CMB makes hard to ignore. More realistic rotating models exist within expanding cosmologies, and they are often discussed in the language of vorticity, shear, and Bianchi-type anisotropic universes. They introduce global vorticity or shear that would imprint anisotropies in the CMB, especially at low multipoles where the largest scale patterns live. A net rotation would produce characteristic signatures, including alignments and temperature gradients beyond what inflationary perturbations predict. It would also affect polarization, because the scattering geometry at last scattering is sensitive to large-scale velocity fields and to any coherent twist in the cosmic rest frame. The CMB is therefore the primary test because it is both ancient and all-sky, and because its statistics are measurable to high precision. If the universe had a global rotation axis, the sky would not be statistically the same in every direction, even after accounting for our local motion. We would expect specific low multipole anomalies that persist across frequencies and instruments, not artifacts that come and go with data processing. We would also expect correlated signatures in E-mode and potentially B-mode polarization patterns, because polarization encodes quadrupole anisotropies at scattering and can reveal subtle large-scale dynamics. Polarization, in particular, acts like a second channel of information, because it is sensitive to geometry in a way temperature alone is not. Thomson scattering produces polarization when the incoming radiation has a quadrupole pattern, and that quadrupole can be shaped by velocity gradients and anisotropic expansion. E-modes are the curl-free component, while B-modes have a curl-like pattern, and different physical mechanisms populate them. A globally rotating universe would not hide easily, because it would tend to produce coherent large-angle correlations that do not look like random phase inflationary fluctuations. Observations do not show the needed signal, and this conclusion has strengthened as measurements improve from COBE to WMAP to Planck, and as ground-based experiments refined polarization maps. The CMB is remarkably isotropic after removing our local motion dipole, and the remaining anisotropies match the expectations of a nearly isotropic, nearly Gaussian field. Tiny anomalies and curiosities exist, but they do not assemble into the coherent pattern required for a global vorticity that could drive galaxy spins directly. Any global vorticity must be extremely small, far below the level that would matter for the dynamics of structure formation. Large-scale structure surveys add independent constraints, and they do so with a different set of systematics and a different physical lever arm. A rotating universe would subtly bias the distribution of galaxy orientations and the growth of structure along different directions, producing anisotropic clustering beyond what is expected from local physics. It could also introduce preferred handedness in certain correlation functions, or alignments in spin directions over enormous volumes. Current surveys find no compelling evidence for a universal axis of rotation, once selection effects, projection biases, and observational incompleteness are accounted for. This does not mean the universe is perfectly featureless, and it does not mean every direction is identical in every respect. It means any global rotation is constrained to be so tiny that it cannot be the main source of the spins we see. The dominant story remains local torque and collapse, not a cosmic whirl, and that is a stronger statement than it first appears. It says the universe can generate abundant angular momentum without borrowing it from a universal reservoir of rotation. So the tension becomes sharper, not weaker, because it forces a layered explanation rather than a single sweeping cause. Angular momentum is everywhere locally, Yet the universe refuses to pick a direction globally, and that refusal is itself an empirical discovery. It is not something we assume for convenience, because the sky could have told a different story. Instead, the data insist on a cosmos that is statistically impartial on the larger scales we can test. One way to understand that balance is statistical, and statistics are often where cosmology hides its deepest intuitions. If many regions acquire angular momentum through tidal interactions, their spin vectors will be distributed across the sky, shaped by local environments rather than a global directive. Some will point one way, some the opposite, and many will be tilted at every angle, with correlations that fade with distance. The vector sum over a large enough volume tends towards zero, even when individual magnitudes are large, because random orientations cancel. This is not a loophole in conservation, and it is not a trick of language. It is conservation operating in a universe with many independent interactions, where the bookkeeping is local and the averaging is global. Each torque is paired with a counter-torque somewhere else, often in the surrounding mass distribution, and sometimes in the relative motion of filaments and sheets. Angular momentum is exchanged between protohalos, filaments, and the larger tidal field, and the accounting closes only when the full region is included, like balancing a budget that spans an entire economy rather than a single household. Inflation strengthens this statistical cancellation story by removing large-scale preferred directions, making the initial conditions close to isotropic and random phase. If the observable universe began from a small smoothed patch, then any residual global anisotropy would be tiny, diluted beyond practical detection. The remaining perturbations would be random phase fluctuations with no built-in axis, and that matters because axes are what global rotation would require. In that case, the default expectation is no net cosmic spin, even though local spins are inevitable once gravity begins sculpting structure. There is also a deeper conceptual issue, and it sits at the boundary between physics and meaning. In general relativity, the idea of a total angular momentum for the entire universe is subtle, because conserved quantities depend on symmetries and on how space-time behaves at infinity. Global conserved quantities are cleanest in spacetimes that approach flatness at infinity, where you can define reference frames far away and compare them consistently. The universe does not have an outside boundary where you can stand and measure its rotation, and it does not offer an asymptotically flat edge for simple definitions. So the question, what is the universe's total spin, is partly a question about what definition is physically meaningful. Still, within the observable universe, we can ask whether there is an effective large-scale vorticity, and we can ask it in operational terms. We can ask whether the cosmic fluid has a coherent swirl relative to the CMB frame, and whether that swirl shows up in temperature, polarization, and the distribution of structure. The answer from data is that any such swirl is extremely constrained, and it is constrained in multiple, independent ways. The universe behaves as if it has no preferred rotation axis on the largest scales we can test, and that behavior is consistent with inflationary smoothing. That conclusion does not trivialize the ubiquity of spin, and it does not make rotation less important. It makes it more interesting, because it forces a two-level explanation that connects the earliest physics to the later complexity. Locally, angular momentum is generated and amplified by gravity acting on asymmetry, and it becomes visible as disks, jets, and orbital systems. Globally, symmetry and inflationary smoothing keep the average close to zero, so the cosmos remains directionless in the statistical sense that observations demand. This is the climax of the documentary's logic, and it carries an almost paradoxical elegance. The universe can be filled with spinning things without itself spinning, because the source of spin is relational and local rather than imposed from above. Angular momentum is not a substance poured into the cosmos from one direction, and it is not a cosmic wind that blows everything into rotation. It is a conserved bookkeeping quantity that emerges whenever forces act with a lever arm in an asymmetric environment, and the early universe guaranteed a symmetry at some level through quantum fluctuations. The early universe provided the raw ingredients, and each ingredient plays a specific role in the chain of causation. Quantum fluctuations supplied the initial irregularities, tiny differences in density and gravitational potential that could be amplified later. Inflation stretched them into a nearly scale-invariant pattern while suppressing large-scale rotation, leaving a universe that is smooth yet textured. Expansion cooled the plasma into atoms and released the CMB as a fossil record, a snapshot of a time when the universe was only about 380,000 years old. Gravity then amplified tiny density differences into the cosmic web, where tidal torques generated the first spins in forming halos. From there, the story cascades, and each step is a transformation rather than a replacement. Halos acquire angular momentum through their environment, and their merger histories can reorient and redistribute that momentum. Gas inherits that angular momentum and settles into disks, but feedback from star formation and black holes can move angular momentum around and sometimes eject low angular momentum gas. Stars and planets inherit angular momentum through collapse, accretion, and collisions, and their spins can be altered by tides and impacts. Even compact objects inherit and redistribute angular momentum through mergers and radiation, with gravitational waves carrying away angular momentum as well as energy. So the opening hook returns with new weight, because it is no longer just a poetic claim. You cannot stand still because motion is built into the way structure forms, and rotation is one of the most efficient ways for gravity to store dynamical information. Yet the cosmos, taken as a whole, appears eerily impartial, with no universal spin axis to point to, no single direction that the sky prefers. The universe is full of whirling systems, but the background they emerge from remains, in the statistical sense, astonishingly even-handed. Cosmic balance is not a mystical equilibrium, and it is not a hidden intention in the laws of nature. It is the outcome of symmetry, inflationary smoothing, and statistical cancellation across immense scales, combined with the unavoidable generation of local torques in a lumpy universe. The universe generates rotation everywhere because asymmetry is unavoidable in a fluctuating field, and because gravity couples everything to everything else through long-range forces. The universe avoids a global rotation because the largest scale initial conditions were smoothed and randomized, and because any remaining coherent vorticity is constrained to be tiny. Transition. We return to the philosophical edge, where conservation explains the accounting, but not the first reason the ledger exists. In the final chapter, we confront the deepest version of the question, the one that remains even after the mechanisms are understood. Why does angular momentum exist as a fundamental conserved quantity at all? And why is it tied so tightly to symmetry and the laws of physics? Why does quantum spin come quantized as an intrinsic label, while cosmic spin emerges from relational gravity and the geometry of collapse? And why does the universe look like a machine that produces endless rotation, yet refuses to choose a direction for itself, leaving us surrounded by motion inside a cosmos that, on the largest scales, stays almost perfectly unbiased? Stand still for a moment, then notice the trick in the instruction, because motion is the default state. You ride Earth's spin beneath your feet, and you ride its orbit as it cuts a wide ellipse around the Sun. The Sun itself drifts through the Milky Way, and the Milky Way rotates inside the local group's slow gravitational dance. Even the matter in your body carries a quieter kind of turning, quantum spin built into the identity of particles. The central question returns in its sharpest, most unsettling form. If spin appears at every scale, why does angular momentum exist at all? And why does the universe, taken as a whole, seem to have no net spin? This chapter closes the ledger, not by adding a new force, but by connecting the entries already on the page. Quantum spin sets the microscopic rules of identity and stability, and it does so with mathematical rigidity. Gravity and dissipation amplify tiny twists into fast rotation during collapse, turning small initial conditions into visible structure. Dark matter builds the scaffold that holds galaxies together and preserves their angular momentum history over cosmic time. Early universe physics sets the initial conditions and constrains any global cosmic rotation, leaving little room for a preferred axis. We start at the smallest scale, because the story begins before stars, disks, and even atoms become ordinary. Particles carry intrinsic spin, which is not literal spinning matter like a tiny top. Spin is how a quantum state transforms under rotations, and it arrives in quantized units fixed by representation theory. Electrons are spin 1/2, meaning a full 360-degree rotation does not return the wave function to itself. It takes 720 degrees, 2 full turns, for the quantum phase to come back exactly. Photons carry spin as helicity, with polarization encoding how the field twists as it propagates. These facts are not optional details of chemistry, and they are not decorative abstractions. They determine atomic structure, magnetic moments, selection rules, and the stability of ordinary matter. If you could see the microscopic world as a visual field, the imagery would be strange and precise. A cloud of electron probability would not be a bead orbiting a nucleus, but a standing wave with angular patterns. The atom's shape would be a map of allowed angular momentum states, each one a solution to a rotationally symmetric equation. Spin couples to orbital motion through relativistic corrections, splitting energy levels into fine structure. That splitting is measurable as spectral lines, and it becomes a fingerprint for elements in stars. In practice, the cosmos announces quantum spin through light, and we decode it through spectroscopy. The Pauli exclusion principle ties directly to spin, and it prevents matter from collapsing into a featureless heap. Fermions cannot share the same quantum state, so electrons build shells and atoms have size. This is why a table is solid to your touch, and why chemistry has a periodic structure. Without exclusion, electrons would all fall into the lowest energy state, and atoms would shrink catastrophically. Degeneracy pressure in white dwarfs and neutron stars is also a spin story, because it is a consequence of fermionic statistics. You can compress a fermion gas, but you cannot force all the particles into the same state. Pressure appears not because of heat, but because of quantum bookkeeping. Even the 21-centimeter hydrogen line used to map galaxies depends on a spin flip. In neutral hydrogen, the electron and proton can align their spins or oppose them, and the energy difference is tiny. Yet over vast clouds, rare transitions accumulate into a detectable radio glow. That line becomes a cartographer's ink, tracing spiral arms and galactic rotation far beyond visible starlight. The documentary's scales are different, but the currency is the same. Spin, counted in discrete units at the bottom and in sweeping rotations at the top. Spin is conserved because the laws of physics do not care which way you face. Rotational invariance means experiments give the same results after a rotation, whether you turn the apparatus or the entire coordinate system. Noether's theorem turns that indifference into an accounting rule, and it does so with surgical clarity. If the laws are symmetric under rotations, angular momentum cannot simply vanish. Conservation is not a moral statement about nature, and it is not a cosmic promise. It is the measurable price of symmetry in the equations, paid out every time a system evolves. Historically, this idea did not arrive as a single revelation. Classical angular momentum emerged from Newtonian mechanics and the geometry of central forces, and it became a practical tool in celestial calculations. Noether, in 1918, showed that these conservation laws are the shadow cast by symmetry itself. That shift matters, because it explains why the ledger is so strict. We conserve angular momentum not because we chose to, but because the universe refuses to privilege one orientation over another. That explains why angular momentum is protected once it exists, but it does not yet explain why everything seems to have some. The next link is amplification, and gravity is the amplifier. When a cloud collapses, its moment of inertia shrinks, and rotation speeds up. The ice skater analogy survives because it is the same mathematics, and because it is the same constraint. Collapse turns a slow, barely measurable twist into a fast, dynamically important spin, and it does so without asking permission. In the real sky, collapse is messy, and that messiness is the point. A molecular cloud is turbulent, threaded by magnetic fields, and sculpted by shocks from nearby stars. Its density is clumpy rather than smooth, so gravity pulls harder in some regions than others. Those uneven pulls generate torques, and torques convert irregular motion into organized rotation. A cloud that begins with almost no coherent spin can still end with a disk because the environment refuses to be perfectly symmetric. The universe does not need a master crank to turn things, it only needs slight imbalance. The key is that energy is easier to lose than angular momentum. Gas can radiate heat away quickly, and shocks can dissipate random motion into thermal energy that escapes as photons. Angular momentum is harder to erase, because removing it requires a torque or a way to export it to something else. In plain language, you can cool a cloud faster than you can stop it from turning. Disks form because collapse cannot proceed straight inward while keeping the same spin. The system finds a compromise, and the compromise is rotation supported in a plane. Visually, this is where the ledger becomes cinematic. A diffuse cloud contracts, bright knots ignite, and a thin, luminous disk sharpens like a blade. Dust lanes appear as dark brushstrokes, and the disk's rotation becomes readable in Doppler shifts. The plane is not chosen by aesthetics, but by angular momentum's direction, one vector that defines an axis. Around that axis, matter settles into orbits, because orbiting is the cheapest way to keep spin while losing energy. In star formation, the disk is not a decorative byproduct. It is the mechanism that processes angular momentum, moving it outward so mass can move inward. Magnetic turbulence and instabilities transport angular momentum through the disk, often described through an effective viscosity. The magnetorotational instability in particular turns weak magnetic fields into a powerful conveyor of angular momentum. Jets and winds act like exhaust, carrying angular momentum away while allowing accretion to continue. The result is a star that forms at all, plus planets that inherit the leftover spin budget. That inheritance is not gentle. Collisions, resonances, and migration can rearrange where angular momentum lives within a young system. A planet can trade orbital angular momentum with a disk, spiraling inward or outward depending on the torque. The star's spin can be braked by magnetic coupling to the disk, preventing it from spinning up to breakup speed. Even in a quiet-looking planetary system, the ledger is active. Mass moves inward, angular momentum moves outward, and the books must balance. Compact objects show the same ledger with extreme numbers, where the familiar becomes almost unrecognizable. White dwarfs and neutron stars spin rapidly because collapse shrinks the lever arm dramatically, and conservation does the rest. A neutron star packs more mass than the Sun into a sphere the size of a city, so a modest initial rotation becomes milliseconds per turn. Pulsars spin down because they radiate energy and apply electromagnetic torque to their surroundings, sweeping beams through space like lighthouse lamps. Their timing is so stable that tiny deviations become data. Glitches reveal superfluid vortices, where angular momentum is quantized in a macroscopic quantum state. The star's crust and its superfluid interior can rotate at slightly different rates, storing stress in the coupling between them. When vortices unpin and rearrange, angular momentum is transferred abruptly, and the pulsar's spin jumps. Black holes add frame dragging, where rotation twists spacetime itself and shifts the orbits of nearby matter. Even there, the story is bookkeeping, with angular momentum carried away by jets and gravitational waves. When black holes merge, the final ringdown encodes the remnant's mass and spin, as if the universe signs the receipt. Transition. Individual stars can become near-perfect spin machines, but galaxies rotate as coherent systems across tens of thousands of light-years. Galaxies make the ledger visible, because their rotation curves measure gravity directly. We watch spectral lines shift across a disk, red on one side and blue on the other, and we translate that pattern into orbital speed. The flatness of those curves shows that most mass is not in starlight, because outer stars orbit too fast to be held by visible matter alone. Dark matter halos dominate the potential and stabilize fast outer orbits. The halo is not just extra mass added to fix a plot. It is the long-lived reservoir that stores much of the system's angular momentum and shapes how baryons settle. The visual signature is almost paradoxical. The luminous disk fades with radius, yet the rotation stays high, as if an invisible hand holds the outskirts in place. Gravitational lensing adds another layer to the picture, bending background light into arcs that reveal mass where no stars reside. Structure formation simulations, seeded with tiny early fluctuations, produce halos whose angular momentum is distributed broadly, with baryons cooling into the inner regions. In that sense, a galaxy's visible spin is the bright tip of a darker rotational iceberg. The best current picture is not that galaxies were born spinning like rigid wheels. Their spins are acquired during formation through tidal torques, mergers, and anisotropic accretion. Neighbouring density peaks pull unevenly on a protohalo, applying a net torque over long times. The torque is strongest before collapse, when the object is large and the lever arm is biggest. Later, conservation turns that modest early twist into fast rotation as matter contracts, and the direction becomes an inherited axis. Mergers complicate the accounting, but they do not erase it. When two galaxies interact, their orbital angular momentum can be converted into internal rotation, random motions, and tidal tails. Some encounters spin up disks while others heat them into spheroids, redistributing angular momentum into stars on more chaotic orbits. Gas, because it dissipates, can settle back into a new disk after a merger. carrying a memory of the net angular momentum that survived. The ledger does not promise a single outcome, but it demands consistency across the exchange. Gas then falls into the halo and cools, shedding energy while keeping much of its angular momentum. That is why thin disks exist at all, and why they are fragile records of past torques. Bars and spiral patterns redistribute angular momentum inside the disk, moving it outward and reshaping density profiles. Resonances act like gears, transferring angular momentum between stars and patterns in the gravitational potential. Feedback can remove low angular momentum gas and reshape the inner mass profile, especially when supernovae and stellar winds drive outflows. Yet the outer rotation still points to the same conclusion. A galaxy's visible spin is a tracer of a deeper, darker structure. The cosmic web extends the same logic beyond single halos. Filaments feed galaxies along preferred directions, and that can imprint weak statistical alignments in spin relative to large-scale structure. Clusters grow by directional infall, carrying orbital angular momentum that becomes internal motion and turbulence in hot intracluster gas. In X-ray images, that gas can show sloshing patterns and pressure fronts, hinting at the angular momentum of past mergers. None of this requires a global cosmic rotation. It requires only that the universe is not perfectly symmetric on small scales, which we know from the CMB's tiny fluctuations. Transition. To understand why galaxies rotate the way they do, we return to the beginning, where the first asymmetries were written. The early universe sets two constraints that shape the ending of this story. First, it provides unavoidable fluctuations, because quantum fields cannot be perfectly still. Even in a vacuum state, fields exhibit zero-point fluctuations, and inflation would have stretched those fluctuations into macroscopic seeds. Second, it strongly limits any overall rotation, because the universe looks nearly isotropic. Inflation, if it occurred, would have stretched space so rapidly that any pre-existing large-scale vorticity would be diluted. The CMB then becomes a test, because global rotation would leave distinctive temperature and polarization patterns. Those patterns would not be subtle in principle. A rotating universe could imprint anisotropic correlations, twisting the alignment of polarization modes and introducing preferred direction signatures. Observers would see a systematic swirl in the statistical properties of the microwave sky, beyond the simple dipole caused by our motion. The data do not show those patterns at a level that could matter for galaxy spins. After removing our local motion dipole, the CMB is remarkably uniform, with fluctuations at roughly 1 part in 100,000. That uniformity is not boring, it is a constraint with teeth. That does not mean the universe has zero vorticity in every possible definition. It means any coherent, observable global rotation is extremely small, far below what would be needed to drive the spins of galaxies directly. The universe refuses to pick a preferred axis on the larger scales we can measure, and it does so with stubborn consistency. If there is a cosmic spin, it is hidden beneath the sensitivity of our best maps, or it is defined in a way that does not produce an observable axis. So why does everything spin if the universe does not? The answer is that local angular momentum is easy to generate and hard to erase. Tiny asymmetries are inevitable in a fluctuating universe, and they are amplified by gravitational instability. Once matter clumps, torques arise naturally because real structures are lopsided and environments are uneven. Dissipation removes energy efficiently, but it leaves angular momentum behind, forcing rotation into the surviving structures. In other words, the universe can be globally impartial while still being locally untidy. The second part of the answer is statistical cancellation. If many regions acquire spin through local tidal interactions, their directions will vary. Some spins point one way, others point the opposite way, and most point somewhere in between. Add enough independent vectors, and the sum tends towards zero, even if each individual vector is large. This is not a philosophical escape hatch, but a property of random walks in vector space. You can have a universe filled with spinning systems and still have no global spin axis. There is also a deeper caveat, and it matters for intellectual honesty. In general relativity, defining the total angular momentum of the entire universe is not always well posed. Global conserved quantities are cleanest when spacetime has the right symmetries and boundary conditions, such as asymptotic flatness. An expanding universe does not come with an external reference frame at infinity, and it does not offer a natural boundary where you can sum everything cleanly. Asking for the universe's total spin can be like asking for the total northward direction on a sphere. The question can depend on how you define the bookkeeping surface and on which symmetries you assume. Still, within the observable universe, we can ask operational questions, and those questions are testable. Is there a preferred axis in the CMB beyond known systematics and foreground contamination? Do galaxy spins show a coherent handedness across the sky, beyond selection effects and survey geometry? Do large-scale flows reveal a universal swirl relative to the CMB frame? So far, the best answer is no at meaningful levels, and the null result is itself informative. The cosmos behaves as if it is globally unbiased, even while it builds local rotation everywhere. Now we return to the hinge that links every chapter. Angular momentum exists because the laws are symmetric under rotations. That statement is powerful because it turns a philosophical idea into a quantitative rule you can test. Symmetry is not just aesthetic, and it is not merely a preference for elegant equations. It is an engine that produces conservation laws, and conservation laws shape what structures can form and survive. When a system cannot shed angular momentum easily, it must reorganize into disks, jets, rings, and orbits. But the deepest wire remains open, and the documentary should name it clearly. Why do the laws have these symmetries in the first place? Why is space-time locally Lorentz invariant and rotationally invariant to such precision across energies we can probe? Why do quantum fields come with spin representations at all? And why do fermions and bosons divide nature so cleanly? We can describe the consequences with extraordinary accuracy, from magnetic resonance to stellar evolution. We do not yet know the ultimate reason the symmetries hold, or whether they emerge from something deeper. Dark matter remains part of that unknown, because it dominates the mass and likely much of the angular momentum budget. We infer its presence through rotation curves, lensing, and structure growth, and those lines of evidence converge with uncomfortable agreement. We still do not know its particle nature, its interactions, or whether it carries additional structure beyond gravity. If dark matter has self-interactions or warm velocities, it could subtly change how angular momentum is distributed in halos, smoothing cores or altering substructure. The scaffold is real, but its material is still unnamed, and that ignorance limits how complete our ledger can be. There is also a deeper frontier at the boundary of quantum theory and geometry. Quantum spin is intrinsic, while classical rotation is relational and emergent, defined relative to other things. Some approaches to quantum gravity suggest spin and space-time geometry may be linked more directly than we currently understand. Spin networks, torsion in space-time, and gauge symmetries hint at connections, where rotation becomes part of the fabric rather than motion within it. Yet no single framework is confirmed, and no experiment has delivered a final verdict. The ledger might have a deeper accounting system beneath it, but we have not opened that book. So the final synthesis is not one mechanism, but a chain. Symmetry gives conservation, and conservation protects angular momentum once it exists. Quantum mechanics writes spin into the identity of particles and the stability of matter, shaping atoms and the chemistry of worlds. Gravity amplifies tiny twists during collapse, and dissipation sheds energy while leaving rotation behind. Tidal torques and mergers distribute angular momentum through the cosmic web, with dark matter halos acting as long-term reservoirs. Inflation and isotropy constraints keep the universe globally directionless, while statistical cancellation keeps the net close to zero. This resolves the paradox without dissolving the mystery. Everything spins because asymmetry is unavoidable, and angular momentum is hard to erase once structure forms. The universe seems not to spin because the larger scale initial conditions are nearly isotropic, and any global vorticity is tightly constrained. The local and the global can both be true, because conservation works in parts while averages cancel. The ledger balances in the aggregate, even while every page is full of motion. We return to the opening hook with a different meaning. You cannot stand still because the universe builds structure by storing motion in rotation, and it does so across an absurd range of scales. From an electron's spin state to a pulsar's millisecond clockwork to a galaxy's slow turn, the same conserved quantity threads through every scale. Imagine a match cut that begins with a quantum measurement, then widens to a disk around a newborn star, then widens again to a spiral galaxy turning in darkness. The cosmos keeps its books with relentless consistency, even when the entries are scattered across light years. The final answer is therefore two answers layered together. Physics explains how spin persists and propagates through symmetry, conservation, and structure formation. and it explains why dissipation leaves rotation behind. The deeper why points to the origin of symmetries and the initial conditions that inflation and quantum fluctuations set, which we can constrain but not fully derive. Rotation is not an accident added on top of reality. It is part of reality's architecture, a quiet rule beneath the spectacle, and a reminder that the universe remembers every twist. Across this journey, stillness kept dissolving into motion, from Earth's daily spin to the Milky Way's slow rotation, and onward to the hidden turning inside atoms. We followed angular momentum as a strict cosmic ledger, born from rotational symmetry, conserved without exception, and endlessly traded between orbits, spins, fields, and light. Gravity then acted like an amplifier, shrinking lever arms until clouds became disks. Disks fed stars. Stars collapsed into pulsars and black holes, and galaxies spun inside dark matter halos that store far more than the visible story suggests. We learned that quantum spin is not a tiny ball rotating, but a rule for how matter responds to turning space itself, quantized in discrete steps and woven into chemistry, magnetism, and the pressure that props up dead stars. We watch disks solve a problem gravity cannot, shedding energy through heat and radiation, while refusing to shed rotation. So angular momentum must flow outward through turbulence, winds, and jets. And we pushed all the way back to the early universe, where inflation stretched quantum fluctuations into the seeds of structure, while smoothing away any large-scale swirl that would leave a preferred cosmic axis. That is why the sky looks so even, and why the cosmic microwave background down to parts in 100,000 tells us the universe has no meaningful global vorticity. Yet that same near-perfect symmetry does not forbid local twists, because a universe can be directionless in total, while still allowing equal and opposite spins to form everywhere. In the cosmic web, tidal torques, mergers, and anisotropic infall can generate and redistribute angular momentum without ever creating net spin from nothing, leaving galaxies and halos to remember the environment that shaped them. The open edges remain, and they matter, because the ledger explains how spin is preserved and shuffled, but not what wrote the first entry. We still do not know whether dark matter's unknown microphysics quietly sets the angular momentum budget of halos, or whether subtle alignments of galaxy spins across filaments will become a clean, statistical fingerprint of cosmic formation. And at the deepest layer, we are left staring at symmetry itself, asking whether rotational invariance is fundamental, or an emergent feature of a deeper theory, where quantum spin and space-time geometry finally share one accounting. In the end, rotation emerges as the universe's hidden architecture, not a decorative detail but a structural principle, spanning quantum rules, gravitational collapse, and the growth of galaxies. Everything that forms must negotiate this constraint, because energy can be lost, matter can cool, light can escape, but angular momentum demands a balancing act. The result is a cosmos filled with spinning worlds and whirling stars, threaded by disks and jets, and organized by halos we cannot see, yet can measure through their gravitational pull. What began as a simple observation, nothing is ever truly still, became a unifying map of how nature keeps its promises. From the stern, Gerlach split to the flat rotation curve. From a pulsar's glitch to a black hole's ring down, each chapter was a different way of reading the same signature. The universe does not spin because it prefers a direction. It spins because its laws are symmetric, and symmetry makes conservation unavoidable. So the paradox resolves into a kind of elegance, and also a challenge. Local rotation is not evidence of a globally rotating cosmos, but evidence that tiny imbalances can be amplified, stored, and exchanged, until structure itself becomes a record of those early, almost imperceptible asymmetries. The universe can be, in the large, astonishingly close to zero, while being, in the small, endlessly busy, like a perfectly balanced scale whose pans are never empty. The story, then, is not, where does all the spin go, but how does it keep getting organized? Conservation does not demand stillness, it demands bookkeeping, and gravity is the accountant that turns microscopic irregularities into macroscopic, enduring motion. Even the most violent events we know, from supernovae to mergers, do not break the rule, they simply move angular momentum from one place to another, sometimes all the way into space-time itself as gravitational waves. That brings us back to the question that opened this film, the one you felt in your own body as we name the motions you ride every day. If almost everything spins, why does angular momentum exist at all? And why does the universe's total spin seem to balance to nearly zero? It exists because the laws of physics do not pick a preferred orientation, and that symmetry forces a conserved quantity to exist, while the near-zero total follows naturally if the early universe had no global axis for one direction to win. In other words, the universe does not need a master rotation to produce rotating things. It needs only symmetry, fluctuations, and time. Then gravity and collisions do the rest, building countless local gyroscopes whose vectors mostly cancel in the grand sum. The cosmos can be full of spinning parts, and still be, on average, eerily impartial. And yet the deepest why remains just out of reach, which is exactly where good science lives. Why is rotational symmetry so exact? Why does quantum spin exist as a basic label of matter? And what deeper framework makes those facts feel inevitable rather than merely observed? Perhaps the final answer will come from mapping spin alignments across the cosmic web, from pinning down dark matter's identity, or from a quantum theory of gravity that treats rotation not as motion through space, but as a property of space. For now, the closure is this, and it is enough to carry with you. The universe is not a single wheel turning in the dark. It is a vast balance of countless rotations, each one real, each one conserved, and together adding up to almost nothing. Everything spins, not because the cosmos leans one way, but because symmetry gives it no choice, and because gravity turns the smallest whisper of imbalance into the architecture of worlds. If you want to keep following that architecture, look up the next time you feel still, and remember that every calm horizon is built on conserved motion. Then follow the evidence from the polarization of ancient light to the Doppler shift of distant gas, and watch how the universe keeps its ledger. In a cosmos with no preferred direction, the most memorable direction may be the one we choose, toward understanding. You have never been still, and now we can say why. Because rotation is what symmetry conserves and gravity magnifies into structure. The universe can sum to nearly zero spin because it has no global axis to favour, while local twists arise, grow, and cancel through the same unbroken accounting. Everything spins, yet the cosmos chooses no direction, as if reality itself is built to move without ever taking sides. In that balance between endless local motion and global neutrality, we glimpse the universe's quietest, most profound design. If this question stays with you, follow the measurements. CMB maps, galaxy surveys, gravitational waves, because the next clue will be written in how spins align and how they don't.